All right, I think I'll go ahead and get started with the opening remarks. Um, Thanks everyone for joining our online workshop. Very happy to be doing this for these next few days. This topic of quantum Boltzmann machines has been something that's very exciting for me and for several colleagues and for Shin as well. And so it's a nice marriage of Boltzmann machines and quantum computation as I've attempted to depict on this introductory slide. I want to give a special thanks to Professor Xin Wang and his PhD student Chen-Kai Zhu for helping to organize. This is something we've been planning for several months. We've been sending emails to ask invited speakers. So we're very happy to do it online. And we are doing it at a time that is somehow convenient for people on the US East Coast and in China. Um, so that has to do with us being the co-organizers of this online event. Okay, so what was the start of this? Back in June, Shin and I, we were both working on projects in quantum Boltzmann machines, and we've collaborated on many topics in the past before. And so we had a Zoom call, and at some point during the Zoom call, Shin suggested, why don't we have an online workshop? And you can see some email exchange that we had right here. This was me replying to Shin saying, I think this is a very good idea. Let's try to do it. And one point I wanted to emphasize about this field, when we were collecting and searching for invited speakers, we did a very simple thing. We just searched for the key phrase quantum Boltzmann machine in the abstract of submissions in the archive. And this is what showed up last night when I did the search. When I did the search a few months ago, maybe there were 5 fewer papers. And so what you see is that on QuantPH in this field, there are only 48 papers that have quantum Boltzmann machine in the abstract. And so that means this is a very young field. When quantum computing was being formed in the mid 90s, people would talk about back then how you could have all the papers that were relevant in the field on your desk and study them and try to make it advance. At the time, there was like Shor's algorithm paper, Grover's algorithm, maybe some papers on quantum error correction, et cetera. And so I never had that opportunity. I started my PhD in the mid 2000s, and by that time there were many hundreds, if not thousands, of papers in quantum computing. And so for me, it's remarkable to see that there is a subfield of quantum computing and machine learning where there's only 48 papers. I don't know if you could print all these out and put them on your desk, but you could attempt to read several of the important ones and study them. Okay, so I wanted to talk a bit about some of the invited speakers that we have. I'm very happy to see Nathan logged on. So Nathan Wiebe is one of the founders of the quantum Boltzmann machine concept, among many other contributions that he's made to quantum computing. And another founder of this subfield is Mohammed Amin of D-Wave, who we're very happy to have tonight. So he'll log on. I believe he's I don't know the schedule by heart, but he's in the 8 p.m. session for U.S. East Coast time. In British Columbia right now, it's 5 a.m., and so it's a bit too much to ask him to log on so early. Anyway, so we're very happy to have these two founders of this subfield participate. I wanted to mention some other names of invited speakers we have. There's been really within the past year, several papers on quantum Boltzmann machines from various people. I'll just say their first names: Ruchira, Maria, Masahito, Nana, Drumil, Cheng, Adit. So they'll be talking throughout the workshop, and I'm very pleased to have them and to count two of them as collaborators. We're also going to have some speakers talk to us about quantum algorithms for thermal state preparation. If you're working in this field, you'll know that a quantum Boltzmann machine is mathematically the same as a parameterized thermal state. And there's been lots of activity on quantum algorithms for thermal state preparation during the past year or two. And we're very, very happy to have these three speakers tell us about their work on this topic and potentially how that intersects with quantum machine learning and in particular with quantum Boltzmann machines. And the other invited speakers we have are going to talk about related topics in quantum machine learning, um, coming from a variety of different angles, some of which are connecting to quantum Boltzmann machines, some of which are more broadly quantum machine learning. So we have quite a number of invited speakers. I'm very happy that we managed to get such a talented group of people to participate in our workshop during these days. You might have noticed, I'm just going to mention a few logistics regarding the workshop. We're 3 days in total, Monday, Tuesday, Wednesday. Each day has two sessions. We're embarking on the first session right now. 4 talks per session. It's best if each speaker limits the talk to 25 minutes to allow for 5 minutes of questions and transition. I don't know if we actually got the word out about that, so but we'll keep you on track. Um, and what we did recently is we've made time for discussions after each session. I think it's going to happen where many people have many questions that will not be able to fit into the few minutes between talks. That certainly will be the case for me. And so after each session, we've allocated an hour, and so stay as long as you have the patience for it afterwards. And the idea is to ask more questions about the slides and scope out open problems and possible future collaborations. So that part I'm very excited about. And this is a notice for the speakers. All the talks are going to be recorded and posted to YouTube. If you don't want that, send us an email and let us know. Okay, with that, um, I'm going to hand it over to Nathan. Thanks so much for giving a talk to us. So if you don't mind to share your slides.
Wonderful. Thanks a lot, Mark. And thanks a lot for choosing such a good photo of me online. Or you could have picked a lot worse ones.
Sure, yeah. I should introduce you. So Nathan is a professor at University of Toronto and has made many significant contributions to quantum computation, quantum machine learning, quantum simulation, and beyond. And so you'll likely see his name pop up a number of
Oh
times
yeah, this one looks
throughout
good.
the talks this week. Okay, so I think everyone is curious to hear what you have to say, Nathan. So why don't
Wonderful.
you go ahead
Thanks a
and
lot, Mark.
start?
My biggest regret is that I'm definitely not going to have enough time to say all the things that I wanted to say. So I'll try to go through the important points about this, while also um, considering taking advantage of the fact that I'm the first speaker, so I know I'm kind of obligated to spend a little bit more time than would normally be allocated, talking about the basics of quantum Boltzmann machines, as well as why I feel that this has actually been a substantially understudied part of quantum machine learning for often what I feel are the wrong reasons. So let me kind of get into what's going on high level, there's kind of a broader question that we should ask about this whole field. There's a number of different reasons why quantum machine learning may be of interest or should be of interest to a number of people. To me, there's a number of different reasons why it's an important field to end up studying. To me, the most important question, excuse my cell phone, the most important question to address is really how does learning actually end up working in a quantum setting? It's really interesting, I feel, because of the fact that in quantum settings, there are different ways that we can meaningfully end up encoding information, not just in bit strings, but also in amplitudes. And figuring out the right way of balancing the flexibility and power that we end up getting through interference between the amplitudes in a quantum distribution, and also the repeatability and the clonability, in some sense, of bit strings gives us this tension in designing a model that ends up meaning often that figuring out the right way of translating a machine learning model over to the quantum world is entirely unobvious. And for these reasons of understanding how we can learn from quantum states and or compress quantum processes using ideas in machine learning, that to me is the most important aspect of QML because it can't be replicated at all by machine learning, traditional machine learning methods. Because if you wanted to transform a quantum state, you'd have to do tomography in order to try to replicate it. And in that case, you killed kind of the setting. The next is that people are, of course, especially in industry, more interested in is trying to find advantages that yield computational or sample advantage relative to classical methods. This aspect, while still an important question going forward, is something that actually has broken my heart time and time again in quantum machine learning, because often we end up finding that the advantages that quantum ends up giving for these types of problems are modest at best. So understanding this is, of course, a vital area because a big advantage from quantum computers could revolutionize the impact that they end up having in machine learning. However, at the moment, it's very difficult to argue for more than a modest polynomial advantage for classically relevant problems. But the other aspect that I think is also under emphasized is how important quantum information theory ends up being to quantum machine learning. Actually, I'll be so bold as to say I feel that actually many of the problems people in QML struggle with these days are often problems that people like Andreas Winter ended up solving in the early 2000s. Because actually, if you think about it, a quantum neural network is nothing more than a parameterized quantum channel. And often what we're actually interested in is understanding how much relevant information can be sent from Alice, say the input units in a neural network, to Bob in the output units of the neural network. And so from this perspective, it actually is a really nice playground that allows us to use results from information theory to understand the limitations of what machine learning models can actually end up doing. So these are some of the ideas behind it. But at a high level, the central idea that really has dominated. Now, I want to emphasize this is not the only idea in machine learning, but this is one of the central ones that really has ended up making the explosion in recent years of ML possible. And this is the idea of deep networks. And the idea basically behind this is that what we are interested in is what's known as a neural network. And a neural network, it has very little other than spiritually to do with the neurons in our brain. But it kind of models something similar in the following way. What it tries to do is it tries to build a hierarchical understanding of different objects through a layered network of neurons. Each of these neurons basically is a register that stores an activation. The simplest activation is just on and off, right? 0 or 1. But in general, for an ordinary neural network, this is often just seen as a number that we end up having. And the way that a neural network ends up working is each neuron is connected to sets of neurons in the next layer of the neural network. And then from those individual input activations that end up coming in the bottom, the output activations are set through some type of an activation function. Then what we do is we take a look at the top layer of the neural network and make all our decisions based on that. And so the idea basically behind deep learning is to end up interpreting each of these different layers of the neural network as a different hierarchical representation of information to kind of model how we think about classifying images. So like if, for example, of course I've got, for those of you who know me, of course I've got a Coke bottle right next to me. But the point is, like when you show this, you all know this is a Coke bottle, but if you sit down and think about it, why do you know it's a Coke bottle? Well, after some thought, you could start saying, well, I know that Coke bottles have this red tag in the middle with black text around the outside and have kind of this curvy shape going up to a cap on the top. But all of these are very high-level features that are different from the low-level pixel information that's entering your eyes. So at some level, what your brain is doing is it's taking these low-level features that are coming in of pixels and translating these into high-level features that then you can interpret in order to be able to make a decision about the cokiness of this image over here. So that's what artificial neural networks have tried to do. And obviously, they've revolutionized the world. And through ideas related to these, as well as applications of these in the form of transformers, we've ended up having things like ChatGPT, which has literally changed the world, and for better or for worse, changed science. But the basic idea behind this is that and this is the vital part about the whole thing, is that the system has to be trainable. The particular edges and the weights of all of these edges inside this graphical model, which define the activation function, those are not set a priori. Those are actually learned by providing samples to the network. And then what we wish to do is we wish to optimize a particular objective function in order to be able to figure out what the best weights are to maximize that. And in particular, that could be, like, say, for a classification task, it would be, say, given a set of cat images on the bottom, we'd like to output the probability that the high-level outputs, say, a single neuron that decides whether it's cat or not cat. We'd like to be able to make sure that it maximizes the probability of outputting cat when a cat example is given and minimizes the probability of saying not cat when a not cat example is provided. So this is the example that I like going with Boltzmann machines. Yes, and for the Quantum Boltzmann case, it will of course be, instead of a cat image coming in, it'll be kind of more of a cat state coming in, but we'll get to that in a moment. But from a perspective of classical machine learning, cats are actually an absolutely vital part of the whole of machine learning, because of the fact that neural networks are frequently trained on image data as part of the corpus that ends up coming in. And image data is usually taken from the internet, which is 90% cats. So cat images are something that neural networks in practice are often amazingly good at dealing with because of humans' obsession about our furry little friends. But anyways, the basic idea behind a Boltzmann machine is that a Boltzmann machine is sort of one of the most natural models that you can think of as a physicist. What you do is you take a series of individual neurons that describe your neural network, and then what you'd like to do is you'd like to build some type of an energy function on top of it. Then what we would like to do is we'd like to say, okay, for the joint distribution over all of the neurons, we set the probability of those neurons to be proportional to the exponential of an energy function. So it's up to you to decide what the energy function actually ends up being, but you choose an energy function, and then you define the probability of this to be equal to, well, e to the minus energy divided by z, the partition function. And the whole task about this is to find the best energy function in order to maximize the probability of the network correctly predicting the relevant information about the cat images coming in. And so the way that we end up doing this is let's imagine what we were doing is we were training it with a bunch of these images over here. So, we have a bunch of different animals here. I've got two pictures of cats, and I've got two pictures of not cats. What we'd like to do for our energy function is we'd like to make sure that if we provide an image of the cat, the energy should be very low, corresponding to the cat being correctly labeled. But the cat being incorrectly labeled, saying it's not a cat, we should have a very high energy associated with it. Similarly, if we have a dog, we would like to be able to have that dog image classified as not cat. And similarly, we like to have a low probability of a possum being classified as cat, because, well, if you bring a possum home from the pound one day, you'll probably be quite disappointed. The most common model that we end up taking a look at in Boltzmann machines is really, for an energy function, just an Ising model. So basically what we do in the Ising model is that we just end up saying, okay, let's treat each of the neurons inside the neural network as a series of bits that are 1 or 0. And then we have a series of weight functions corresponding to it. And here, of course, in general, I could end up putting in bias terms that only depend on one of the weights, but I've ignored that in the energy function here just for simplicity. Then what we do is, in order to find this, what we need some kind of a loss function. The typical loss function that's chosen is that we would like to be able to we would like to be able to minimize the KL divergence between the probability distribution that is generated by the Boltzmann machine and the training distribution that we use to put on it. So we basically end up throwing in a bunch of examples that correspond to the labels that we're interested in. And then we try to figure out what the difference is between the two. And the KL divergence is really an important concept because the KL divergence between two probability distributions can be used to bound the single shot distinguishability between two probability distributions. So that's one of the reasons why we really like this notion. And also because of the fact that it turns out that the KL divergence acts really nicely in concert with a Boltzmann distribution because of the logarithms inside playing well with the exponentials of the energy. So this is basically it. And if we want to talk about this in terms of spin language, this leads to the following Hamiltonian that we end up having corresponding to it. And so this is an example of an early Boltzmann machine where it was trained with a bunch of these images over here. And Boltzmann machines are naturally generative. When you run the Boltzmann machine, it will generate a whole bunch of new images based on the previous ones. And yes, by the standards of course, modern neural network, these modern neural networks, these generated samples are kind of laughably bad compared to what ChatGPT can do. But one of the things that I want to emphasize is that the Boltzmann machine was developed even before backpropagation. And one of the reasons why it became so popular is because gradients were extremely difficult to compute on neural networks of the day. And Boltzmann machines actually have relatively easy gradients to compute, but they run into other issues that I'll speak to later. So as mentioned, the biggest reason was because, well, it's an early model of neural networks that could be used to on early computers where backpropagation was not practical to do this. Another thing that's really great about the Boltzmann machine is that it's, well, naturally generative. Unlike early neural networks and things that don't end up resembling an autoencoder, typical neural networks are not naturally generative. However, the Boltzmann machine is, which is a really kind of nice feature to think about it. The other thing that's really nice about it is the objective function that we end up using in this is super well motivated. And also Gibbs distributions play really nicely with it. So the expression for the derivative of your training objective function, i.e. the KL divergence, is actually easy to compute. In fact, it's easier to find than the KL divergence. But the reason, though, that I think is most relevant to this community is the fact that it's physics inspired. And in turn, because it has a Hamiltonian, it's by far the easiest neural network model to convert into a quantum neural network model. And one of the things I want to mention about this that's actually really important is that, well, the Boltzmann machine ended up being very important in the beginning of machine learning. In fact, Geoffrey Hinton goes so far as to say the most impactful thing that Boltzmann machines ever led to was him getting tenure. One of the reasons why people end up using them less is because gradients are extremely expensive to compute using Boltzmann machines. In particular, gradients need to be estimated using sampling, which leads to an order 1 over epsilon squared number of samples that we need to compute the gradient, where epsilon is the magnitude of the gradient that we need to compute. So this ends up meaning that if we had a gradient of 10 to the minus 7 that we needed to estimate, then we would need about 10 to the 14 samples to deal with this. And because deep neural networks tend to have substantial gradient decay problems, this ends up leading to Boltzmann machines actually not being able to deal with very deep networks. Also, they end up running into problems where gradients can be very small if the weights are randomly chosen. This was partially dealt with in the community by coming up with mean field approximations to the Boltzmann machine as an initial guess for the weights. But this was a horribly bad problem that has actually been rediscovered in the quantum machine learning literature, where it's now known as a barren plateau problem to us. The other problem is, well, there's no kind of fast back propagation algorithm for this because of the order 1 over epsilon squared optimal training methods, and also that approximate thermalization methods are needed because what we need to do is we need to prepare our probability distribution that goes like e to the minus energy. So this means that we need to find a way of doing that. And it turns out that that is really difficult to do exactly. So approximate methods are needed, and these approximate methods in some cases may not actually be theoretically well known to converge in general. However, actually pretty much all of these problems exist to one degree or another with existing approaches to quote unquote quantum neural networks. And as a result, I feel that actually the quantum Boltzmann machines have really been unfairly maligned in the community, leading to people suspecting that, oh gosh, well, because nobody uses a Boltzmann machine classically, why should we ever use them quantumly? Because it just seems to more and more people in ML think that this was a bad idea. But in the quantum setting, as I was mentioning, all of these problems don't have an easy solution. And so, well, the Boltzmann machine really, I feel, should still be more strongly considered for this. So to figure out how we would quantize a Boltzmann machine, it's very simple. What we basically do is we take our training data set and replace that with a density matrix, i.e. a quantum distribution over the training. We take the energy function for the Boltzmann machine and replace it with a quantum energy operator, a Hamiltonian. And instead of the KL divergence, we replace that with a quantum relative entropy between two distributions. And then the result of the quantum Boltzmann machine now is no longer a probability distribution. Now it's a quantum thermal state. And what we aim to do is we aim to build a quantum thermal state that's output by the Boltzmann machine that minimizes the KL divergence between the training data and the generated data from the Boltzmann machine. That's basically at a high level. A major problem that ends up coming in with the Boltzmann machine, though, in practice, ends up being that the individual Hamiltonian terms that you use in the quantum Boltzmann machine don't commute. This can end up leading to a lot of problems in coming up with good methods to compute gradients in this case, because differentiating these models is quite difficult. Now, an opportunity, though, on the other hand, for a quantum Boltzmann machine is that classically we could only play with the energy function that we end up using in order to be able to decide cat versus possum. However, if we're looking at the quantum machine learning case, we have two aspects that we can change. We can change the energy function directly, but we can also change the eigenbasis that the data is represented in. And this creates an opportunity because while it gives us more freedom to be able to describe a distribution, it also creates a challenge because of the fact that we lose many of these commutation properties that make finding gradients for our training objective function easy. Okay, so another thing, I don't have as much time to get into it, is a question of whether or not Boltzmann machines are kind of more expressive. In some sense, they are, because you can prove BQP completeness for it. And the way that this ends up working is you can embed the clock state into a low temperature thermal state for a Boltzmann machine and end up bootstrapping it from that. But the training process that we end up looking at for this is by essentially what we do is we use gradient descent on the quantum relative entropy between this, which is the distance between, it's kind of a statistical distance between two quantum distributions given by the following. And here, in this case, sigma is the state that's generated by the quantum Boltzmann machine, which is defined to be e to the minus Hamiltonian, where the WJs are the weights. These are your free parameters that you're adjusting in order to be able to set your particular model that you want. And we want to choose this to minimize it. And this divergence here, it's not technically a distance, but this divergence between the two quantum density operators is zero if and only if the two are equal to each other. So this means that we can actually literally use a quantum gradient descent in order to be able to hit an optimal. And if we get zero, then we know for sure that the two distributions are literally equal to each other. One challenge, of course, is that, we have to end up considering what the logarithm is. For the case of the all-visible Boltzmann machine, I'll discuss the hidden case hopefully later. This is really easy because of the fact that the first term is just simply a matrix exponential, and we take the logarithm of a matrix exponential trivially. The denominator is just a scalar, and so we can just find the logarithm of that. So differentiating this log sigma term that we end up getting with respect to w is very easy because, well, we only have the derivative of the first term is trivial, and derivative of the second one isn't really so bad in the all visible case. Also, the rho log rho, the entropy term for the training data, is independent of the weights W. So if we want to optimize this, we can actually even ignore that term and only look at the trace of rho log sigma, which is known as the cross entropy term. And so the derivative with respect to the weights of log sigma is just this. So we end up getting an expression for the gradient of the entropy as the average value of the individual Hamiltonian term given by the model, and minus the average value of the Hamiltonian term over the data, which ends up matching the distribution that we would end up seeing classically from the same thing. So that's what you end up getting out of this. There is one technicality that ends up coming in. You have to remember when you're doing this derivation that the chain rule doesn't apply when you're taking a derivative of the trace of the exponential. So a little more work needs to be done in order to do that. But interestingly enough, because of the cyclic property of the trace, you end up getting the average value over the data, which coincides with the classical expression for the gradient in the case where you're dealing with all visible units. So the number of times that we need to access the Gibbs state, i.e. this sigma, ends up scaling if we wanted to be able to compute the gradient for this as m squared over epsilon squared. This can be improved using a number of different techniques that have been developed since then, but you'll note at a high level, conceptually, this scaling is kind of equivalent to the scaling that you would end up seeing on a classical computer. However, of course, it can be quadratically improved using amplitude amplification if purifications of a Gibbs state are provided. So just to give an idea about how this ends up working, here's an example of a Boltzmann machine that's trained on quantum data coming in. Again, for a quantum Boltzmann machine, we really should always be thinking about the training data being quantum states. So one of the things that's really remarkable I found with this is in practice, if we have the ability to be able to prepare the exact thermal state as a function of the individual parameters, actually the training process is very quick. These are some mixed states over here, and I've given you kind of the standard bar plots of the density matrix corresponding to it. And these are the absolute values squared, I believe, of the individual components. But the key point here is that after only about 5 training epochs, and starting with a random state, we end up with a density matrix that's visibly indistinguishable from the true states in all of these different cases for 2-qubit examples that I've got here. And in principle, we can continue the exact same thing with both hidden as well as visible units. Now, one of the reasons why I mention this is that, if you're taking a look at a traditional neural network, right, we have all of these different layers. These mid layers over here, rather than high-level layers, these aren't used directly in order to be able to make a decision about what the object actually is. And so because these are not used for anything more than temporary variables or latent variables in some sense in the calculation, these are called hidden units over here. And so the question is, they're ignored in a classical computation, how do we deal with them in a quantum case? In the quantum case, if we're going through, the natural thing to do is to just do a partial trace over all of those units. So that's what we've done in this plot. And in that case, training is still possible, but it's a lot more difficult to think about because the gradient expression gets gnarly when you do the partial trace. In any case, something else that's really cool about this is that you can use this a quantum Boltzmann machine to build a quantum associative memory using the exact same thing. So here's an example of 6 qubits over here with a series of different training vectors corresponding to an address. And what we'd like to do is we'd like to be able to get the quantum Boltzmann machine to reproduce the corresponding training vector over here when provided with the given address over here. And these are the generated examples. after, 1,000 epochs. And we can see in both of these cases, actually, it converges to something that's visually indistinguishable from the targets. Now, as I mentioned, training with hidden units works pretty much exactly the same way, except what we need to do is we need to now trace out basically everything but the units that we're considering to be visible. And then what we want to do is we want to now, instead of comparing the whole network, we only want to compare the training data to the output of the Boltzmann machine over here and do a partial trace over all the other variables that we're just using for correlations. So that's basically the thing about it. One of the major challenges is that the logarithm of trace is not equal to the trace of the logarithm, unfortunately. So this ends up meaning that the expressions for differentiation for this can actually be really quite difficult. And chain rule doesn't work, which is one of the key challenges that ends up coming in. Another problem that we end up seeing is that if we end up having hidden units coming in, a problem is that we end up getting entanglement between the hidden and visible units. And what we end up finding because of that is that effectively when we entanglement ends up meaning that our information is non-locally stored in the network. It's not isolated to particular layers. And so then when we throw away intermediate layers, the majority of the information gets lost from the neural network. And we end up getting a result that typically is like 1 over the dimension. This is an analog of the barren plateau problem that ends up coming in. So when we're designing quantum neural networks with hidden units, we really want to be able to deal with too much entanglement in the problem. One solution, which isn't widely discussed in the literature but is known, is the possibility of choosing your system in such a way so that the interaction Hamiltonian that you pick between your visible and hidden subspaces, if that interaction ends up commuting with the hidden variables, then basically no entanglement can end up getting generated between the two registers. And that's vital because of the fact that when we end up doing a partial trace, it doesn't actually end up leading to effectively decoherence, or as people would say in the barren plateau literature, a barren plateau. So things like this, in order to be able to selectively use entanglement to handle the parts that you want, i.e. like the density matrices that are genuinely quantum that are being put in, is a good idea. But we have to, when designing a good Boltzmann machine, manage entanglement in order to make sure it's doing something useful. So skipping through that, there are expressions that can be found for the gradient of the relative entropy for a Boltzmann machine. And one of the simplest ways of doing this is to deal with variational upper bounds on our objective function and then minimizing them, in which case we can end up getting simple expressions out of this. And we end up finding that in the event that the partition function is large for our quantum system, that these algorithms are efficient. One of the big challenges, which others are going to speak to later, is that all of this ends up depending upon our ability to be able to prepare a thermal state for this. And the thermal state basically is extremely difficult to prepare. Actually, in general, if we could prepare thermal states for an arbitrary Hamiltonian, then BQP would contain QMA, which is, of course, believed to not be true in general. So thermal state preparation is a hard and likely unanswerable problem at some level. However, approximate versions of training are possible and can empirically perform well. But again, we still don't know necessarily how good theoretically it needs to be in order to look at this. One of the things that I want to mention here is that we can also get around this rather than variational upper bounds by training with respect to Rayleigh divergences. So these have the property that Rayleigh 2 divergence in particular ends up upper bounding the Rayleigh 1 divergence. And so these have the advantage that they involve the logarithm of trace, not the trace of the logarithm, which ends up making the gradient much easier to deal with in the case where we have hidden units present in the whole thing. Also, we can end up proving that these barren plateau issues don't actually end up showing up for Rayleigh divergences in the same way that they do in conventional quantum machine learning. One of the reasons why is that we have a logarithmic objective function here. So in the event that the probabilities are small, the logarithm ends up partially dealing with that and can boost the gradients up to something large. So you don't get the unconditional barren plateaus that you end up seeing for most other models using this approach. Nonetheless, it still is a very good idea to be careful about vanishing gradient issues because, after all, for all quantum methods, traditional gradient optimization scales like 1 over epsilon or 1 over epsilon squared, depending on if you're using quantum approaches. And this means that even modestly small gradients are going to lead to large computational cost. And in turn, you can go through and end up computing very complicated expressions for gradients of this that end up holding. And the standard way of dealing with gradient of these Rayleigh divergences is to truncate this infinite sum at some particular order. One thing that I want to mention is in the few minutes that I have left is how we can end up doing this optimization. Traditionally, what people have looked at in the past is doing optimization through gradient descent on a classical computer. That may not actually be optimal because each gradient estimation that we end up needing is going to take order 1 over epsilon squared calculations, or in this case, order 1 over epsilon cubed calculations for this gradient. And we'll have to repeat that conceivably a large number of times before the algorithm ends up going down. And in turn, the value of epsilon that we need provably is going to actually lead to polynomially worse scaling and conceivably could need an exponentially large number of steps, depending on the other parameters of the optimization. So that's a major issue here, this epsilon scaling, because this is in the inner loop of the training process. This can be a killer. And this is one of the things that ended up killing everything on the classical side, because we needed just such a large number of examples. But recently, new approaches have been found for doing optimization in quantum computers that skip this and move the optimization over to the quantum computer itself. So no measurements are ever done using these approaches. And the basic idea behind this is that what you can end up doing is you can end up doing the following. Let's imagine you wanted to do optimization in the following way. What you have is you have a situation where you have an objective function that you want to optimize. We build a dynamical system that has friction in it. So the friction here, first we have a potential function, f, that we would like to minimize. This would be our training objective function. And so if we take a look at this dynamical equation, what we would have here, and x would be the weights of the Boltzmann machine. What we would have here is we would have, say, a situation where we initialize these weights at some particular value, and hopefully they're close to a local optima. And then if we just simulate this dynamical system, friction will end up causing it to fall into the corresponding nearest local optima. Then if we just measured the x values, we would get the optimal parameters for this. This can actually be translated into a time-dependent Hamiltonian, believe it or not, by using ideas from cosmology. Actually, it turns out. So the following time-dependent Hamiltonian over here is fully conservative, can be implemented on a quantum computer, and will simulate friction. So the idea basically is that what we end up doing is by simulating the time dependence of this frictional Hamiltonian, what we can end up doing is we can end up building a unitary evolution that will simulate the optimization process. And you could show that the scaling that you end up getting in this as a function of epsilon is actually super polynomially better than the scaling that you would end up getting by sampling. Because in this case, we just need to simulate the friction Hamiltonian and use ideas from phase kickback or block encoding in order to be able to output the training objective function from the Boltzmann machine. And this allows us, again, to circumvent the biggest problem that's been plaguing Boltzmann machines. And so for this reason, I feel that actually Boltzmann machines are really kind of ripe for a little bit of a new revolution, because thermal state preparation methods have gotten vastly better over the last few years, and these optimization methods can solve the 1 over epsilon case. And finally, quantum Boltzmann machines, unlike parameterized quantum neural networks, as they're often called, they actually really are a direct analog of the classical neural network. And so from that perspective, I feel that the Boltzmann machine is actually a better place to begin and think about comparing up against classical learning in a quantum setting because of the fact that it is well motivated And also it is a true quantum neural network. So to conclude, I wanted to just leave with some open questions, and I apologize for not being able to get too deep into many of these particular things. If anybody has more detailed questions, I'd be happy to handle them during a discussion later. But one of the big ones is, yeah, I feel is if we're taking a look at the quantum Boltzmann machine, it's really kind of nice because of the fact that we work with Gibbs states, which kind of end up giving us a maximum entropy or the maximum uncertainty estimate that we can end up getting for a given value of the mean objective function in some sense, or the mean energy. So that's one of the reasons why Gibbs states are great, but they're extremely hard to compute. And so, question is there a more efficient one that we can end up taking a look at that, say, perhaps only ends up looking at local expectation values rather than minimizing something global? Um, the next question is, what are the roles of hidden units? How important is the residual entanglement between the hidden and visible units inside a quantum Boltzmann machine? In theory, it can be catastrophic. However, the better training that we end up getting using some of these gradient descent ideas that have recently been come up with might actually obviate some of the problems that are created by these sorts of barren plateaus. Another issue is that nobody really has kind of looked at a good end-to-end cost analysis of training a quantum Boltzmann machine. And I'd like to understand what that ends up looking like in order for it. Further, what about properties of the Hamiltonian itself? Are properties of particular Hamiltonians, such as area loss or topological protection of states, useful for designing quantum neural networks? In fact, actually, in principle, you can always end up thinking about a single qubit quantum error correcting code as being a binary classifier. And so, from that perspective, there may actually be a really nice link between some of these topologically protected features in Hamiltonians and machine learning by choosing our Boltzmann machines to reflect those. Also, understanding quantum Boltzmann machines from an information bottleneck perspective could be really interesting to look at how information ends up flowing in some sense between the individual layers of a quantum Boltzmann machine and help us understand how the structure of a quantum Boltzmann machine ends up leading to its predictive power. Finally, one thing that I'm kind of interested in also is that the quantum Boltzmann machine suffers from the problem that the Gibbs state preparation in general is a QMA hard problem. However, if we have if we have side information that's provided to a user, the thermalization of a system need not necessarily be hard if we have a sufficiently good prior over what that thermal distribution ends up being. So there may be ways that, similar to how public key cryptography ends up working, we can actually leverage the very hardness of Gibbs state preparation in order to be able to come up with a more secure version of quantum machine learning using some of these ideas. But in general, I think that the biggest thing about quantum Boltzmann machines is that it really provides us with a very clear example of what a quantum neural network ought to look like. And by studying this in more detail, it's my hope that the community will actually be able to not only clarify what a quantum neural network is, but come close to answering my ultimate question of what learning even means in quantum settings. Thank you very much.
Thanks a lot, Nathan. That's a very insightful talk with many important points raised. It sounds like you're going to be available for the discussion session in an hour and a
Yes.
half. So since you have negative 10 minutes left for your
Oh,
talk, I
shoot.
suggest
I'm really sorry, everybody.
I didn't want to interrupt you because it's recording, and I think someone who would be listening to it later would be annoyed. Like, who's that guy interrupting Nathan saying all these interesting
Oh, God,
things?
no, you should have interrupted me,
Um,
Mark. I'm so sorry, people.
let's reserve all questions for Nathan, which I think there'll be many for the discussion session. And thank you for nice talk. So our next speaker is Christa Zoufal. Christa's here. If you wouldn't mind sharing your slides.
Yes, absolutely. Give me 1 second.
So Christa is an expert on quantum machine learning and beyond, who is at IBM Quantum in Zurich. And she's going to tell us about Gibbs state preparation, which is an important problem for quantum Boltzmann machines and quantum computing more generally. I think you have to hit swap displays because we're seeing the
Perfect.
presenter.
Yeah. I
Yeah.
was about to ask if you see the correct view. Oh, no, that's this one. All right. Do you see the
Yes,
right
that
one?
that
Yeah?
that we see it. Perfect.
Okay.
So
Love.
please go ahead.
Yeah, thanks so much for having me present here. And I think this now fits perfectly post Nathan's talk because, as he already said, the approximate Gibbs state preparation is also something that where there's potential to do it, like also rather in the near term, and we've understood so much about the general preparation capacities, and this really nicely flows into the whole topic of quantum Boltzmann machines. And today I'm going to speak exactly about approximate Gibbs state preparation with a very specific ansatz construction now that employs what we call dynamic parameterized quantum circuits, and I'll give you an overview right now, right? So this work is based on a paper that we've put on the archive last year. If you're interested, we're still in the process of getting it into the channel. But if you're interested in more of the details and also like the derivations of the respective bands that I'm going to show you later, this is where you can find it. And of course, a big thank you to all of my collaborators, specifically Abhinav, who's put like so much work and so much of his genius and mind into this work. Good. So what I'm going to talk about is I'm first going to talk about this dynamical parameterized quantum circuits and why there are specifically interesting ansatz classes for approximate Gibbs state preparation. And then I'll give you two examples of Gibbs state preparation, which are based on different cost functions, which then in terms have a bit of a trade-off with respect to accuracy versus resource costs that go into them. Good. So, starting off, I guess most of us here are familiar with the topic of barren plateaus, but just to recap it really quickly, right? In most of the approximate state preparation methods that we know how to do with near-term quantum computers, we will face some parameterized quantum state where we need to train the parameters in one way or the other. And for most of the methodology that we are aware of right now, these training methodologies lead to this barren plateau phenomenon, like an exponentially flat loss landscape, which is unfortunately the other coin of the side that we have a very expressive landscape and representation to play with. Reasons for that can be that we're close to a geodesign, hence i.e. very expressive, or we have a global observable, or extensive entanglement paired with partial traces or particular noise models. Good. But so this is now really an issue when we talk about like any type of like parameter training in a quantum ansatz model. So what is it that we're actually looking for? Well, we want to have something that's trainable, which usually refers to non-exponentially vanishing gradients. We want to have a model that provides us sufficient expressivity such that it can represent something interesting, where interesting mostly also refers to a system that's not trivially classically simulable. Now, why is this model that we're looking at here interesting? Well, because first of all, we can prove that it does not suffer from barren plateaus at random initialization. We have numerical evidence that it can represent interesting states, and there is also a proven worst case hardness result that we can relate to this model, such that there are indeed some quantumly interesting systems that we can represent with the model. But full disclosure, we're also fully aware that the model is likely to be average case easy. And then there comes again in the question of whether one can make use of classical resources to support the preparation of something that's quantumly interesting, so to say. Great. Oh, and one additional note, and I'll highlight this a couple of times throughout the presentation, is that one thing that's particularly interesting about the system is that we can have a smooth transition where the transition is guided by a simple classical optimizer between the setting where we know that we're provably bare plateau free and where we're provably hard, hence where we can represent the quantumly interesting states. Good. So what's the model that we're looking at? So this looks like what you've probably seen a couple of times, parameterized unitary ansatz, right? What's different here? Well, we do have those purple boxes in between, which are now non-unitary operations. We consider them as dynamic operations. So basically here we see that we consider for the 2-qubit gates that they're either parameterized or non-parameterized, but they're unitary. And the single qubit gates here, they're now non-unitary. What does this mean, or like what are we looking at? So as this non-unitary operation can of course have different forms. What we are considering here and what we've worked with is in its basic interpretation a probabilistic feed-forward operation. With the probability of the feed-forward operation F being controlled by a rotation, if you want to look at it in the purified picture. So let's take a look to the right? If we purify, then we can consider that we have here now like a virtual auxiliary qubit, which is not in here. And on this auxiliary qubit, we apply a parameterized Rx rotation. And this Rx rotation, and in turns, it describes whether we apply our feed-forward operation F or whether we don't. In the remainder of the work, specifically in the numerical experiments, the feed-forward operations that we have looked at is a simple reset. So if like the control here decides if this is a 0, like if the target qubit is a 0, then nothing happens. If it's a 1, then it's simply being reset to 0, i.e. the projector is being applied onto it. Good. Now, potential applications for this are either ground state search, where the idea is that maybe by going also for a non-unitary loss landscape, we can find some shortcuts in the optimization landscape, or for thermal state preparation, which is interesting because a lot of the approximate thermal state preparation that has been looked at with parameterized ansatz circuits has used unitary circuits as the basis, which is of course not directly perfectly suited because thermal state preparation usually is a non-unitary transformation and or quantum process learning. But we'll focus now on the thermal state preparation here. Good. Really quick, what are dynamic circuits? Well, basically dynamic circuits include the possibility of conducting mid-circuit measurements with real-time classical compute, such that we can actually compute feed-forward operations, which are then based on the classical information from the readout. And as many of you may know, this is something that is possible with today's quantum hardware already. So it's something that we can really implement today. Good. These mid-circuit measurements have, of course, like not been first of all like studied for parameterized ansatz circuits, but we do know that they're crucial components of quantum error correction operations, of helping reduce gate overheads for specific entanglement routings by making use of quantum teleportation. For example, you can make use of it for circuit knitting, hence combine quantum resources that are available to larger experiments. You can prepare some topologically interesting states like GHZ states with significantly less gate overhead, and you can also use it to basically represent a particular form of measurement-based quantum computing. But here now we're looking at the properties of why this is an interesting variational ansatz and how it can be applied to Gibbs state preparation. Good. So really quickly also to give a comparison of this to existing non-unitary architectures, also for full disclosure, we're not the first ones to work on this and to look into this. There have been a couple of other works. One example are quantum convolutional neural networks, which have a provable absence of Baron plateaus. Unfortunately, here for those cases where we do know that barren plateaus don't occur, we also know that we can simulate them relatively easily classically. Then there's quite a bit of interesting work also around making use of dissipative dynamics as part of also like a resource in a quantum neural network setting. Now, this is, I would say, also relatively close to what we have been studying. However, what's the big difference here? Now, we're somewhat able to simulate dissipative dynamics in a rather controlled setting. Good. Then another research study that's quite closely related is some interesting work around non-unital noise and parameterized quantum circuits. And again, also the non-unital noise can be viewed as somewhat of a specific instance of a dynamic parameterized quantum circuits, but again, without the lack of control over what's happening within the system. So now I'm coming back to a point that I've mentioned before. One thing that's very important in our construction is that we can interpolate between a very expressive setting and a BP-free case. Good. Yes, and there's a couple of other architectures that have been considered numerically for shallow state preparation, but let's focus on what we've done here. Good. Now to come to the proof and to outline like why barren plateaus are provably not occur for a random initialization. In order to make the statement, we need to have an understanding of this feed-forward distance. So basically, if we consider like one measurement here onto one qubit at the end of our circuit application, the feed-forward distance corresponds to the shortest path from a qubit measurement to a feed-forward operation. When now we consider the feed-forward operations being those blue boxes, and to make things now even a bit more complicated, we're looking at the maximum of the shortest paths from a qubit measurement to a feed-forward operation. Good. Now, based on this feed-forward distance, we can make our statement, namely that for a dynamic parameterized quantum circuit with random initialization, such that the two qubit gates are drawn from a locally scrambling ensemble, and assuming that the two qubit gates are random, then we can state that the variance of the cost function is bounded with respect to the locality of the Hamiltonian and this feed-forward distance, so the maximum shortest path. And finally, we have the Hilbert-Schmidt norm that relates to our Hamiltonian. Good. Now, to give you a bit of an intuition of what this feed-forward distance refers to, it basically illustrates the information spread that is possible within our circuit. So if we go back, right, if we consider this feed-forward operation here now to be a reset, then you can basically also consider it as a cut off of information. So what we can do here is we can somewhat of artificially construct a shallow version of the ansatz where the shallowness of the information spread of the information light cone can be controlled through a tuning of the parameters in the system. And this can be done automatically by a classical optimizer. Good. Now, just really quickly to mention this, right, like this gradient variance also holds under certain noise assumptions, so that's good, we're happy about that. A couple of notes. So this is very important to note. So just because we don't have barren plateaus, that doesn't mean that we can train, especially to the optimal point. There may even still be local minima, or our ansatz may not be able to actually represent the optimum or necessary points within the training trajectory. the bounds that I've just shown you on the gradient variance are independent of the number of qubits and the actual depth of the circuit, but notably, again, it crucially relies on the locality of the Hamiltonian and this feed-forward distance, hence the placement of our feed-forwards in the example of reset operations. If you want to have a bit of a context of how we prove this, so a lot of the proofs around Barron plateaus make use of like dynamical Lie algebras or CX calculus. We used his StatMech model, which is quite nice because it gives us an understanding of basically it provides a representation in terms of a random walk, where each operation defines a transition matrix, and then we can have a look at basically the center of convergence of the random walk, which in turn defines our gradient variance. Basically, eventually we can count the significant number of ones in large Hamming wave distances. But so far so good. For more information, yeah, please refer to the paper that I've shown before. Good. So now a few words on the expressivity. So why do we know that this is an ansatz that can represent non-trivial states? Well, we can make the argument quite simple, in fact. We can consider a unitary circuit of depth d, and then we place in between every now and then our dynamical feed-forward operations. And if we also remember, right, that we can control these dynamical feed-forward operations with parameters. Now, if we set the parameters of our purple boxes such that there is no action, then this circuit basically corresponds to a unitary circuit of depth d. If we make d very, very large, then basically everything holds that we know about deep unitaries, i.e. that we can prepare interesting pure states with this type of architecture. Good. And this, again, like provides this nice connection about this interpolation properties, namely that by having a model that tunes the parameters of how the feed-forwards are applied, we can have a smooth transition between the Barron plateau, provably Barron plateau free, and the very complex scenario. And then again, in the ideal case, the hope is, which needs to be verified on more extensive numerical experiments, that this allows us to start training with good gradients and then moving throughout the training into very quantumly interesting systems. But to comment on the hardness, well, as mentioned before, what do we have here? Yeah, as mentioned before, right? If the parameters are set such that the feed-forwards don't act and we have a very, very deep circuit, then again, like all of the hardness proofs that we know about unitary circuits apply here. But we are aware that since this is a worst case statement, and given the positive technical results that we have around Barron plateaus, it's quite likely that this model is average case, easy to simulate. And this is also something very interesting to study, right? How these components could then come together. So if we are in a parameter regime where we can simulate the model classically, we could also make use of that and simply just use classical resources to provide the gradient for the training and then look for parameter updates, which are not so trivial to establish anymore with a classical computer and then actually execute on a quantum computer. Good. Here we're becoming a bit philosophical about the, I want to say, dilemma that has been discussed quite a bit also recently around the training of parameterized quantum circuits, namely that there's a lot of uncertainty around the fact whether whatever system has non-negligible gradients is also easy to simulate. However, like in this case, that this may even be true, but it's not even necessarily a bottleneck because we do have this possibility of interpolating between these two regimes. And I'm more than happy to discuss with anybody here, but I think that a model can be quantumly interesting as soon as we do need to evaluate like a few states that need to be accessed throughout the training trajectory, which cannot be trivially simulated classically anymore, but for which we need a quantum computer. Good. Now let's have a look at some numerical simulation results for Gibbs states. So here we did prepare a state for an XY model with the circuit construction as you've seen it before, right? We have our blue probabilistic feed forwards and then a set of U of single and two qubit gates, which are also parameterized in between to train. Good. Now, again, full disclosure, the model that I'm showing you here is a very simple one, also quite small, still on a 1D chain for 10 qubits with an inverse temperature of 2. And what we're doing here now, what I'm going to show you is that for this formal state preparation, we considered two different cost function approaches. One of them being a fitting of the infidelity, where we assume that we have access and knowledge of the exact Gibbs state that we want to prepare, and one that is based on variational quantum imaginary time evolution. They do have advantages and disadvantages. Of course, fitting the infidelity and requiring knowledge of the exact Gibbs state, something that's not very well scalable, but enabled us to study the expressivity of the model. And the variational quantum imaginary time evolution approach, while being scalable, is prone to instabilities because the underlying system of linear equations is unfortunately often ill-conditioned. Good. So let's have a look at training the model with respect to an infidelity where we match the exact Gibbs state preparation. So here you can see that we conducted a training over 150 training iterations for different ansatz depths ranging from 1 to 9. Now we have plots that visualize the energy, the infidelity, and the infinity norm of the gradient. Good. What we can see directly here is that the depth equals 1 did apparently not provide us with sufficient expressivity to learn a good model. However, from depth 2 on, we basically see similar behavior, so that should have been sufficient. What we can see here is firstly that the energy converges quite nicely. The same is true for the infidelity. We do get infidelities around the order of 10 to the power -5, which is very nice. And then the last thing that I would like to draw your attention to is the infinity norm of the gradient. So basically here we also see a relatively good gradient behavior and specifically a relatively good gradient size. More specifically, at least on the infinity norm scale, the gradient magnitude does not decrease significantly with increasing system depths. So that was a quite nice sign for us in terms of the training behavior of the model. Good. Now, from these experiments, we do know that the answer is sufficiently expressive, and we wanted to try to push it forward, right? But first, before going to a different cost function, we had a bit closer look at the required depth, because as we've seen here, right, depth 2 was already sufficient for the system size of 10 qubits. And interestingly, this is also something that we would like to follow up on. Depth 2 seems to be already a sweet spot for smaller system sizes already. For whatever system we tried with smaller number of qubits, depth 1 was still not enough. So this is also something which could be worth having more extensive numerical experiments around. Good. Now, as discussed, since the infidelity does not scale, we don't want to spend exponential resources usually, and we don't want to require exact knowledge of the Gibbs state that we want to prepare it. Variational quantum time evolution that is based on McLachlan's variational principle is a scalable alternative. What you're trying to do in this methodology is that you're trying to minimize the error between the variational trajectory and the actual gradient of the system using an ansatz, and we can do it without ansatz, of course. Now, what this ensures is that our parameters always stay real compared to other variational principles, which of course makes it simpler to implement on actual hardware. And unlike product formulas such as Trotter, we can simulate a time evolution, such as imaginary time evolution, which we're looking at for thermal state preparation, with respect to an initial state. And considering this evolution with respect to an initial state gives us the motivation or hope, if you want so, that we require significantly less depth than we would need in tractorized approaches. Good. So, as mentioned before, right, what we're trying to do is we're trying to minimize the error between the variational trajectory and the actual gradient, and that's what this variational principle here tells us. If we solve it, then we get a system of linear equations that tells us how the system parameters of an ansatz that's given need to be evolved such that we're following the time evolution trajectory, in this case, imaginary time evolution trajectory. Now, the quantities that we need to evaluate in this context are on the left-hand side, the quantum geometric tensor, which is proportional to the quantum Fisher information, and on the right-hand side, an operator that's proportional to the energy gradient of the system. Good. Now, here we can have a look at some example runs. We did try to work on thermal state preparation here for two different temperature settings, one that's a little bit warmer and one that's a little bit colder. Now, what we can see right away here is that the infidelities are significantly worse than what we've seen before with the fidelity matching. So evidently the cost function is quite a bit unstable. The energy matching also suffers and the accuracy is not really great. What is good, what gives us hope is that we do observe here that the training behavior is better for larger temperatures, which is also what we would expect because training systems with lower temperatures is usually more difficult. So that is directly reflected by the methodology. But there's obviously quite a bit of engineering improvement that could still be done. So caveats and criticisms, also like to put our cards on the table, right? These are small-scale experiments. The number of systems that we tested also for ground state preparations were at most 12. And even in numerical approaches, like if our gradients are not too small, it might still be that we could see an exponential scaling if we go to 100 qubits. We haven't tested with any shot noise. All of the simulations that I've shown you here were with tensor network simulations, and also not executed on hardware or considering hardware noise. Although this would be a next step that we're looking into at the moment. And finally, there is the scalability versus performance trade-off that we've seen in the state preparation that I've shown you. So we do know that the expressivity is there, but the McLachlan's variational principle did not give us the greatest results. So what I'm specifically interested in looking at is trying different cost functions here because I do think that the ansatz has promise, but we need something that's not as volatile to numerical instabilities to actually get to really good results. And now to give you a bit of a comparison of what I mentioned in the beginning of what we actually want and what did we achieve here. So we did say that we do want to have in all of like the variational training, so to say, or approximate parameterized quantum ansatz training. We want to have a model that's trainable. And here we do know provably that we are barren plateau free for randomly initialized parameters. So that's good. We do want to have an ansatz that's sufficiently expressive, and we do have the numerical indication that this is given. And finally, we want to have a system that's not trivially classical simulable, and we can make use here of our worst case hardness statements also to suffice the setting. So outlook, yeah, what I think is really interesting here is also the component that there is possibly some parameter regimes where we do have classical simulability. And I would be very interested in understanding also more formally whether these regimes can be used to lead us to something that's quantumly interesting and quantumly hard. And I think that that's a question that's of interest to many of us here today. And finally, I want to scale up the experiments here, get more heuristics in to get a better understanding of what's needed, test different cost functions, as mentioned before, and identify a minimal viable experimental setting that we can run on the hardware to also study the impact of hardware noise here in the system. As mentioned, the basic hardware capabilities are there, and so we should be able to execute something on the hardware and get a better understanding. And with that, I would like to thank you for your attention. If you have any questions, please feel free to ask.
All right. Thanks a lot for your talk. I think you have to get going in 3 minutes. Is that right?
Yeah, exactly. Unfortunately,
So
it's
uh,
year end.
let's ask everything that we can to Christa right now, if there are any questions from the audience. I'll ask a question. So at the beginning, you said about how thermal states minimize the free energy, but you were using as your cost function infidelity. Did you, is there any hope to try to use free energy as a cost function? I suppose it's the same as relative entropy.
Yeah, I mean, eventually here we all face the difficulty again of the resources that one requires to compute the free energy, or as you
Mhm.
say, right, the relative entropy in practice. There are some approximations that are quite interesting and that would be potential roads to go down. Um, so bottom line of my answer is the exact one, probably not, but there's hope to use approximations thereof.
Oh, what approximations did you have in mind?
I mean, there's like those forms also that are based, if I'm correct, on alpha Renyi entropies, right? That you
Mhm.
can stack together to get the free energy in place. I I've never tried like how accurate they are. I haven't looked at them also from a theoretical point of view, how accurate of a representation they would be. But as far as I know, they are a bit more feasible to compute also on an actual quantum computer. But if you
Okay,
have any other ideas, I'm super keen to discuss him.
I'll think about it. Any other questions from anyone else among our participants? All right. Feel free to write questions during in the chat. Okay. Well, thanks a lot for your talk and have a good afternoon.
Sure, thank you. You too.
All right. So our next speaker is Dongling Deng. Feel free to share your slides.
Okay, thank you, Mark. Yeah. So maybe let me share my screen first. Can you see my shared screen?
Now we see it.
Sorry. Okay, can you hear me?
Can hear you.
Okay,
Uh,
great.
now
Okay,
okay,
now
perfect.
it works.
Please go ahead.
Okay.
Yeah.
Okay, great. Okay, great. Thank you. Um, yeah, hello everyone. This is Dongling Deng from Tsinghua University. First, I would like to thank the organizers, especially Mark and Xin, for the very kind invitation. Yeah, uh, unfortunately, my own group haven't have published any result on this quantum Boltzmann machine yet. But hopefully, after this workshop, we can have some collaborations. We can. I think these talks are very inspiring. I hope that possibly in the next workshop on quantum Boltzmann machine, I can talk a little bit more about like quantum Boltzmann machine. Anyway, so for my talk, I would like to like kind of talk a little bit more about quantum automated learning. So okay, sorry. Yeah. Okay. Here's my outline. So my group current focus is on quantum AI, quantum artificial intelligence. So maybe I will give a very short, brief introduction to it. Especially, I will talk about some recent work on quantum error correction. So the motivation is that I hope that in the quite near future, we can really run this quantum Boltzmann machine on the real quantum device. Okay. So recent experimental advances on quantum error correction is really exciting. So I want to talk about that. Then I will move on to talk about quantum automated learning. So I will try to convince you that this is a complementary approach to quantum machine learning with the traditional approaches like variational quantum circuits. Uh, then I will give a very brief outlook. Okay. So let's start with these roadmaps outlined by IBM and Google. So if you look at these two maps, they are quite exciting, right? So for instance, like Google, for this Google's map, like in 2015-5, plus they may have like 1,000 physical qubit with logical qubit error rate smaller than 10 to the minus 6. So I think this is quite exciting. If we can really achieve this, then possibly for some like we can really do some useful experiment on the quantum Boltzmann machine, right, on these devices. Okay. Also, like IBM's roadmap is also very exciting. Um, so you may know that one of the most challenging part for building a quantum computer is quantum. We need to achieve quantum error correction, right? So you may already heard that, like those Google's Willows chip, right? So basically, this is I think this is a quite a milestone for building a quantum computer. Especially, I quite like this figure. In this figure, they basically showed that if you can increase the code distance, then the logical error will decrease exponentially. So I think this is an unambiguous demonstration of the so-called break-even. That means after you correct the errors, the logical error will become smaller than your physical qubits. That is really exciting and really important. So this year, they also reported another experiment on this color code. They also achieved break even. For compared to the surface code, for color code, some of the logical qubit is more convenient to implement some logical qubits, right? So that's the advantage. In China, there are also some exciting progress on quantum error correction. For instance, Zhang Pan's group at the USTC, they also demonstrated the surface code with a distance equal to 3 on their Zhouzhang number 2 chip. Moreover, like my colleagues Lu Yangsun's group, in collaborate with Dapeng Yu's group at the South Tech, they also reported an experiment on bosonic code. They also achieved a short break-even in their experiment. Meanwhile, the group from Yale also demonstrated this. Worldwide, there are many other more experiment exciting progresses on quantum error correction, like from ETH, Harvard, etc., etc. So for my talk, of course, due to the time limitation, I cannot cover all this very exciting progress. So today, I want to just report one of our most recent progress on quantum error correction. That is an experimental demonstration of the so-called bivariate bicycle code. This is a special quantum low-density parity check code. And this code was originally introduced by Bravi and his colleagues at IBM. So they published a paper on Nature last year. So in this paper, they basically propose this bivariate bicycle code. Okay, compared to this surface code, the advantage of this bivariate bicycle is that, so for the surface code, the encoding ratio is kind of quite small. You need a d square physical qubit to encode a single logical qubit, right? Then the encoding ratio is very small. However, for this bivariate bicycle code, typically the encoding ratio is much larger than this that for the surface code. Typically, it's like 10 times larger. So in our case, we first found out another bivariate bicycle code. We found the code is a 1844 code. That's what we really showed in our experiment. So moreover, for the bivariate bicycle code, another advantage is that the threshold value, the error threshold value, is comparable to that of the surface code. So you know that for the surface code, the error threshold value is roughly about 1%, right? But for this bivariate bicycle code, the error threshold value is roughly 0.7%. So it's really comparable to the surface code. So that is also a very good thing. However, the difficult thing for bivariate bicycle code is that, so for bivariate bicycle code, you need long-range couplers, long-range couplings. So for surface code, you know that each stabilizer you only have a nearest enable. Each stabilizer, the weight of each stabilizer is only 4, right? You only need nearest couplings. But for this bivariate bicycle code, you need very long-range couplings. So this raises a lot of challenges for its experimental implementation. So in our experiment, we collaborated with Wang's group at Zhejiang University. So we fabricated another new chip. We call it a Kunlun chip. And for this Kunlun chip, we achieved like 36 physical qubits. And we also achieved kind of a torus geometry. That means we indeed have a long-range couplers. We can couple like those two qubits that are far away from each other. This is based on this air bridge technique to get all these long-range couplers. Okay. So I don't want to go to the technical details. Okay, here in the right-hand side of this figure, we show the encoding and decoding circuit for the bivariate bicycle code. In particular, in our experiment is 1844 code. Okay, that means we use 18 physical qubits to encode 4 logical qubits with distance code distance 4. Okay. In our experiment, we run error correction up to 6 cycles, like shown here. So, and we then measure both in the Z basis and the X basis, and then measure the error probability, detect the error probability. Okay. So, as I mentioned, we have 4 logical qubit in total, right, in our experiment. Like the experimental, logical error probability from our experiment is shown in this figure. So you can see that roughly after you do some data analysis, you can extract that in our experiment, what we achieved is that the logical error per logical qubit per cycle is roughly about 9%. Of course, 9% is we do not we haven't achieved break even yet. So if you achieve the break even, then you need to show that with increasing distance, the logical error will decrease, right? Like showing here. So the sub-figure C is basically we did some numeric simulations on this to study how far away are we from the break-even point. So the break-even point is basically this crossing point. So as from this sub-figure, you can see that we are not very far away from this break-even point. We needed to suppress our current error by roughly 13 to 14%. So we are working very hard towards this direction. So yeah, I think I should speed up a little bit. Okay, so this is our current experiment on quantum error correction. I hope in the near future we can achieve break even for our bivariate battery code. Moreover, I think after we increase the performance, improve the performance of our chip, we hope that we can someday we can run this quantum Boltzmann machine on our device. So I look forward to the discussion and trying to I mean, it would be great if we can have some collaborations on this. Okay, so our group majorly focused on the quantum artificial intelligence, so-called quantum AI. And my understanding to quantum AI contains two approaches, two directions, basically. One direction is quantum enhanced AI. That is, how can we use quantum computing to enhance AI to solve intricate AI problems? On the other hand, when we use AI as a tool to solve intricate quantum problems, especially quantum many-body problems. Of course, this is a very interdisciplinary field. Nowadays, there are many every day, many papers comes out, and I think in the audience, many of you have contribute pioneering works in this area. So I'm sorry I cannot cover all these results. Here I only list some of the part of the early days review papers. And also I already gave some talks in different conferences and universities. So if you are interested, please also check those talks online. Yeah. So for the major question I want to take care is how to scale up quantum agents. So if you want to achieve quantum AI advantage, right, then you need to make a large quantum AI agent, like you increase your quantum machine learning system to a large size. However, we have several challenges. Some of challenges has already mentioned by Nathan and Christa in their earlier talks today. So the first challenging is if you increase your model, in the classically we can build, for instance, build a GPT. That's because we have a back propagation algorithm, right? We can calculate the gradient with respect to possibly millions of parameters just at once. However, the situation in the quantum machine learning scenario is very different. In the quantum case, the gradient is with respect to each parameter is obtained basically one by one, right? Can only obtain one by one. Then if your system size is small, it is okay. However, when you increase your system size to to the scale of GPT, thousands of billions parameters, then this cost is too huge, right? The second challenge is the so-called parameterized problem, right? That means the gradient vanishes exponentially with your system size. Then if you increase your system, then typically you can only obtain zero gradient. Then it is really hard to train your quantum neural network. This has already mentioned by Christa in her talk earlier. So we thought about this problem for a couple of years, several years. Then we think we have some progress that was to report to you. So in order to deal with these two challenges, we propose so-called quantum automated learning. So in order to understand this, first let's look at the traditional quantum machine learning paradigm. So I only consider supervised learning for simplicity. For instance, in supervised learning, you have for instance, some images, right? Then you need to recognize those images, whether it is a cat or it is a dog. So in the traditional approach, you first encode your image, image denoted as an X, encode your image, your input data X, into a quantum state. And then you evolve this quantum states with a variational quantum circuit denoted by U theta. Here theta denotes collectively all the variational parameters, right? And then after this, you measure some of the qubits, typically log k qubits. K is how many number of your labels, right? And then you do the prediction, right? In order to train this, this U theta is basically the quantum neural network. It's basically a variational quantum circuit. In order to train it, you basically define some loss function, and then you calculate the gradient of this loss function, and you update these variational parameters in each training steps, right? Then at the end of the day, you end up with some optimum theta star, and then your system, your neural network is trained. And in prediction, in the inference stage, you have some new image like X, and you do the same thing. You encode it into phi-X, and then go through U theta star, and you measure some of the qubit to make the prediction whether it is a cat or it is a dog, right? So then in our new paradigm, the so-called quantum machine automated learning case, now we follow a new approach. That means we do not encode this X into a state. Instead, we encode this X into a unitary. So we just encode it into the unitary. And we start from some random quantum states. and then go through this UX. And we also measure some of the qubits to do predictions, right? Then during the training process, we, in the middle of the circuit, we do some perturbation, and such that after those perturbation, the predicted label, like the target predicted label, will be closer to the targeted label. Okay, this UMY, because we only consider a supervised learning case. You know the label of the label Y of X, so you can do such a perturbation. And then we use another Iw-Qbm X to basically like feedback those perturbation information into the circuit. So, and this consists, this UX and then perturbation, then Iw-Qbm, this consists of one training step, and then train this iteratively to n steps with different input samples. Okay, then at the end of the day, you will end up with some precise star state. Now that means you have a trained model. Okay, your system is already trained. Then how to do the inference? During the inference stage, we start now with the precise star state rather than the random state, and then go through UX. Now this time, this X is the new new data you want to make prediction on, right? And then after this, we also measure the same number of qubits to do the prediction. Okay, so I hope I have explained clearly this approach. Okay, so there are some advantages of this new approach. So as you can see, in this approach, we do not have any variational parameter. That means obviously we do not need to calculate the gradient, right? We do not have any, we do not even have variational parameters. And we also do not have this Baron-Parator problem because we do not have any calculate any gradient, I mean, in the narrow sense, okay? Moreover, you can, as I will explain a little bit later, you can see that the whole training process can be mapped to the imaginary time evolution. So then for this trainability of our model, it is explainable. It has explainable and probable convergence. Okay, and also you can see that this have a universal representation power and a very good generalization ability. All this can be rigorously proved. So from a high level, it is I can draw a similarity between this Heisenberg picture and the Schrödinger's picture perspective to quantum mechanics. So in the traditional approach, basically you have variational parameters. Your variational parameters is encoded in the unitary operations, right? And then you do gradient descent to update your operate like U theta. So in this case, the dynamics happens for the operators. So it's more like a Heisenberg picture. In comparison, in our new paradigm, so we do not have variational parameters. Now we do not evolve like the operate. Instead, what we evolve is a quantum states, like some random quantum states. So it's more like a Schrödinger's picture. Okay, so of course those two pictures are kind of equivalent to each other. They are kind of have the same power. However, for some particular programs, one approach may be more convenient than the other. Okay. So now let me give a physical explanation of this. So in our approach, so for example, a data like sample X, you have a label Yx, let's say equal to a cat, right? Then the targeted or oriented measurement is basically a projection to the label Y. Okay, it's like this. then we can define a Hamiltonian like Hx, and you see this after you can, when you go back this, you basically you measure this, right? Is the basically a projection pi y, and then you go u dagger x and then ux, right? So basically, the Hamiltonian is because you want to define kind of a loss, then you use the 1 minus this thing, okay? You can regard this like u pi u as the probability of obtaining the right label y, right? The correct label y. And then to define a loss function is 1 minus this probability, right? Okay. So then for each updating like each training step, basically you are updating the quantum states as shown in this formula, right? You do a perturbation and then you update the psi, okay? Then after t steps, basically the states evolves to this one, and here capital T is how many training steps you have. And the HS is the average Hamiltonian over all the training data samples, right? So from this picture, you have a clear understand of how and why this our approach works, right? So actually, you can rigorously prove that you will like if you choose some like if your initial states, like random initial states, has a non-zero overlap with the ground state space of this Hamiltonian Hx, then you can prove that this approach will converge exponentially towards the global minimum up to high order corrections, and the average loss is upper bounded by your ground state energy. Ground state Eg means your ground state energy of the Hs is correspond to the minimum loss, and plus some arbitrary small constant c, right? That basically what this theorem says is that you can converge exponentially to the global minimum. Okay. Moreover, if you choose an appropriate learning rate, you can prove that the appropriate number of training steps, then the final state can achieve a near optimum training loss with a constant successful probability. Why we have a successful probability? That's because here we need to do a perturbation, and this perturbation is not a kind of a unitary perturbation. Is because imaginary time evolution is not a unitary evolution, right? So then you need to add an ancillary qubit and do basically post selection such that to achieve this perturbation. So then you may worry that after like several training steps, the successful probability would be exponentially small. But this is not the case, as we can prove in our theorem 2. Okay, I think I'm running out of time, sorry. So we did some numeric simulations on this. You can see like from our experiment, numerical simulations, you can see that like after some training steps, you will have a very good convergence to the like global minimum. I want to stress here that in our numerics, we can see that even 29 trials of running the experiment is already good enough for the process. If compared to the traditional approach, 29 trials may not even enough for calculate the gradient, right? Okay, so I just skip this. Moreover, you may worry that during the training process, during the inference process, like here, so there's a subtlety that for each of the training, you may need to go through the whole process for each of the inference sample. But this is also not the case. You can you can reuse this state after your measurement. Okay, so that's what we show here. That means after you training the model, so for most of the time, the measurement is kind of some gentle measurement. Although the state will be changed, revised a little bit, but it will not destroy the state completely. So you can retrain the state a little bit to achieve this, to pull it back to the precise start state. Okay. Okay. So I hope this can inspire, give some inspiration for the future, how to scale up quantum Boltzmann machines. Here I have some show this. These figures are from Mohammed's paper. Okay, let me give a very brief one sentence outlook. I think at the current stage, we still have a long way to go for achieving quantum AI advantage. We are still at the bottom of this huge mountain at the current stage. So finally, I would like to thank my collaborators, especially Professor Hao Wang's group at Zhejiang University, and also my student. Let me conclude my talk by quoting Picasso. Everything you can imagine is real. With this, I would like to thank you for your attention.
Thanks a lot for that interesting talk and leaving us with such a nice quote. We're actually quite a bit over the time, and so
Sorry.
that's
My
okay.
sorry.
And we didn't want to interrupt you. So I think we should reserve the questions for the discussion session, if you can make that in about half an hour.
Sure.
Okay, our next speaker is Ruchira Bhat, coming from Fujitsu Research. And hi, nice to meet you.
Nice
So
to meet you.
Ruchira's going to tell us about her work with Fujitsu on quantum Boltzmann machines. Go ahead and share your screen.
Yeah, sure. Thanks, Mark.
Sure.
Yeah. So
Perfect. Go ahead.
my screen visible?
Yes.
Yeah. So hi everyone. So good afternoon and good morning based on different time zones. So I'm Ruchira coming from Fujitsu Research India. So first of all, I would like to thank the organizers, especially Mark, for giving me this wonderful opportunity to present my work on International Workshop on Quantum Boltzmann Machines. So today I will give you all a brief idea on one of my recent work in arXiv, which is a variational algorithm, new variational algorithm for Gibbs state preparation, and where we are applying it for many body Hamiltonians, different many body Hamiltonians, and how it is used to improve the training of a quantum Boltzmann machine. So for those who are interested to know more technical details of the work, you can go through our arXiv article. And this work has been done in collaboration with my team in Fujitsu Research India, especially Rahul, Avinash, and Dr. Krishna. So just before going into the technical aspects, I would just like to walk you all through a brief introduction about my research experience and my team in Fujitsu Research India. So about myself, so I joined Fujitsu during 2023. So it has been almost like a couple of years and more. I am a part of Fujitsu. And my research mainly focuses around quantum machine learning algorithms and applications. And before joining Fujitsu, I was pursuing PhD in IIT Bombay, India, where my PhD was around computational condensed matter physics, especially in flow-K topological physics and also understanding non-equilibrium quantum phase transitions. And I also have a brief experience in experimental condensed matter physics, where I was trying to understand different magnetic properties in nanoparticle systems. And about my team in India, so we are actually a pretty young team of 2 years old, 2 or 2.5 years old, and we are a 13-member team. And our office is located in the IT hub of India, Bengaluru. And the main core research teams which we are focusing in India includes QML, quantum algos, quantum applications, and quantum software and error correction. So my focus is mainly around the first three topics. And we also have teams working in AI, ML, and also HPC. So those who are interested to know more about our research and works in Fujitsu Research India, you can visit our website. So with this brief introduction, now I would like to give you all a brief overview of what I would be talking today from the technical side. So I will spend first around 10 minutes or so in introduction to Gibbs state. What are the different or widely used variational techniques for Gibbs state preparation, and some approaches or some scalable approaches which people have attempted. Uh, and then I will tell the motivation for why we want a novel variational algorithm, given that there are different existing techniques for Gibbs state preparation, introduce you all to the proposed framework by us, and finally, we'll conclude by giving the details on how we can include or how we can integrate this new novel variational algorithms for training a quantum Boltzmann machine, variational quantum Boltzmann machine. Yeah, so I think by now many of you might already know what Gibbs state is, and from the previous talks as well as from your background. But still, I will quickly go through it. So the Gibbs state, as all of us know, it represents the finite temperature state of a many-body quantum system, and it is equally hard as preparing the ground state, especially at low temperatures. And the expression for the Gibbs state is generally represented by this density matrix, where beta represents the inverse temperature the related to the Boltzmann constant as well as the temperature. And the application of Gibbs state ranges from modeling the open quantum systems in condensed matter physics to combinatorial optimization problems as well as in quantum machine learning. And there are different algorithms that has been proposed for preparing the Gibbs state, focused for or suited for different eras, which is the NISQ era, which is the near-term devices, which are suited for the early fault-tolerant devices, as well as the future fault-tolerant devices. But our focus will be on the near-term devices, the algorithm that is suited for implementation on a near-term device. And it's a variational quantum algorithm for Gibbs state preparation. And from the application perspective, we demonstrate an application by integrating it in the training of a quantum Boltzmann machine. Before going into the details of our algorithm, I would just like to spend few slides on a few of the existing well-known techniques for variational techniques for Gibbs state preparation. So two of the notable ones are one is Warkite, which Christa has already given a nice introduction, and the second one is the variational quantum thermalizer. So the Warkite version, so to tell briefly, so the idea is we start with a maximally mixed initial state and imaginary time evolve it for some finite imaginary time so that we arrive at the Gibbs state of the system. And generally, since it is a non-unitary evolution, it is not directly implementable on a quantum circuit, but there exist different methods using which we can implement this imaginary time evolution on a hybrid gate-based quantum computer. And this goes with the name of Warkite. The second technique that has been used for preparing the Gibbs state variational method is known as variational quantum thermalizer. So the variational quantum thermalizer, we can consider it as analogous to or finite temperature version of the variational quantum eigensolver. So here also we have a parameterized quantum circuit similar to variational quantum eigensolver, but with extra ancillas because our Gibbs state is a mixed state, unlike the ground state, which is pure state. So here we have a PQC defined with extra ancillas, and we will be minimizing the Gibbs free energy of the system instead of the expectation value of the Hamiltonian, which we will be doing in the ground state preparation. And the Gibbs state is known to minimize the Gibbs free energy of the system, similar to ground state minimizing the energy of the system. So generally, so the Gibbs free energy is evaluated using the quantum circuits on a quantum computer, and the optimization step is performed on classical computers. But since the entropy evaluation of this entropy term is generally difficult on quantum computers because of the presence of log rho. So there are several alternative approaches, certain approximation approaches, which have been used in the literature to approximately evaluate the Gibbs free energy. And I have cited here two such examples. So to tell briefly, so one of the approaches that has been used to evaluate the Gibbs free energy approximately on a quantum computer is known as the truncated Taylor series approximation of Gibbs free energy. So here what has been done is, so this is our Gibbs free energy expression where we have the energy term sitting over here and entropy term in the second part. So this entropy term, rather than evaluating the exact entropy of the system, we can evaluate a truncated Taylor series of the entropy term. So our new loss function, rather than the exact Gibbs free energy, will now consist of the energy of the system or expectation value of Hamiltonian of the system and the truncated Taylor series of the entropy, which consist of the state overlaps, the higher order state overlaps. So this makes it easier to evaluate on using a quantum computer because we know that the expectation value of Hamiltonian as well as this higher order state overlaps can be estimated efficiently. And the paper also demonstrates, or the authors demonstrate the efficient preparation of Gibbs state using this truncated Gibbs free energy as the cost function for two models. One is the Ising chain and the XY spin half model. And another approach, which is generally used to evaluate the Gibbs free energy, is known as quantum variational quantum thermalizer. So this is, I coined the term which is in the paper. So there are different variants of this technique existing in the literature. So generally the idea is, so we want to evaluate the Gibbs state, which is a mixed state. The solution proposed includes using two variational quantum circuits, VQC1 and VQC2. And we will be having an intermediate measurement after VQC1 in order to generate a mixed state at the final stage of VQC2. So to tell it a bit more explicitly, so this VQC, the first variational quantum circuit, when we do the measurements over the first variational quantum circuit, we will be getting some classical probability distributions, which are used to evaluate the entropy term in the Gibbs free energy. And the second variational quantum circuits will create a superposition of the basis states to get a mixed state representation similar to this. So we will be evaluating the expectation value of Hamiltonian at the end of the second variational quantum circuit. Together, this E and S, we will be getting the Gibbs free energy, which will be then optimized using a classical optimizer, and we will be updating the parameters of both quantum circuits. So given this, now the question comes like, why we want a new, or what was our motivation to design a new variational quantum algorithm, given there are a lot of techniques existing in the literature that addresses or that proposes different techniques for Gibbs state preparation. So the main motivation is, so when we look at the workflow of traditional variational quantum thermalizer, which is being used widely in the literature, if we have a Hamiltonian and the corresponding parameter, say H1, then we actually need to, so the workflow includes, we start with a PQC with some additional ancillas. We measure the state, evaluate the cost function using any of the methods which we have explained earlier. And then the gradient of the cost function is evaluated on a classical or quantum computer, and optimization is done using a classical optimizer. So this is the general workflow. And for each parameter of this Hamiltonian, we need to run this entire optimization loop again and again, thus resulting in a higher cost. For each parameterized Hamiltonian, we need to execute it that many times. And the second reason is that generally, when we have the many-body Hamiltonians, parameterized many-body Hamiltonians, as a function of the parameter of this Hamiltonian, they will be exhibiting phase transitions or finite temperature crossovers. And it is very non-trivial to represent the Gibbs state around phase transitions or around the critical points using the general ansatz which are used in the literature. So we need, so there is a need for an expressive ansatz to represent the Gibbs state around these points. So to address these two challenges, we propose a collective optimization based, actually two algorithms which are based on collective optimization. One is a fully parameterized quantum circuit based model known as meta-variational quantum thermalizer. And the second one is a neural network based model, which is known as the neural network meta-variational quantum thermalizer. And the ansatz which are designed in both of these algorithms are also designed in such a way so that they are able to capture the complex correlations arising in the Gibbs state. Yeah. So now to explain briefly about what collective optimization is. So the idea is coming from classical machine learning, where we have different training data, say training data 1 up to n, and corresponding to each of these training data, we have an independent model as well as a cost function defining that model. So the idea of meta learning is we define a global cost function that is able to capture the common features or meta features of corresponding to all this training data. And we perform the optimization over that global cost function. So as a result, what we expect is we will get a meta learner which will be able to predict on new data which is not present in any of my training data samples. So we have used this idea in order to prepare the Gibbs state of a parameterized Hamiltonian. Yeah. So if we look at both of these blocks, so this block A, that is the traditional way by which we are training in order to get the Gibbs state corresponding to a Hamiltonian. So if we consider this as a black box, then if we give as input the Hamiltonian and one parameter of the Hamiltonian, we will be getting as the output the Gibbs state corresponding to that parameter of the Hamiltonian only. So rather than that, in our case, which is this flow diagram B, if we consider this box as if we consider this as a black box, then we can give as input Hamiltonian along with a set of parameters of the Hamiltonian. And as the output, we will be getting the Gibbs state of corresponding to all these parameters of the Hamiltonian without the need for retraining for each parameters of the Hamiltonian. So, and if we look at inside this box, what is happening inside? So first we define some finite set of parameters of the Hamiltonian, and these parameters may or may not be present in my test set. So we take these parameters and we encode it either in a classical neural network or in a parameterized quantum circuit. And both of these blocks are then followed by another processing layer, which is a parameterized quantum circuit. And after this, we measure the state of the system, evaluate the global cost function, define a global cost function and evaluate its gradient, and then perform the optimization over either the neural network as well as the parameterized quantum circuit. So if we look at the structure of so this green box represents my first algorithm, which is the neural network based metavariational quantum thermalizer, and the second one represents the parameterized quantum circuit based meta-VQT. So the green box, the structure of ansatz looks somewhat similar to this. Like we have a classical neural network. In this case, we have considered a simple feed-forward neural network. And we encode the parameters of Hamiltonian here, and which is followed by two different types of PQC layers. One is a hardware efficient ansatz, and second one is Hamiltonian variational ansatz. And in the pink box, there is no classical neural network. Rather, we are encoding the parameters directly into the hardware efficient ansatz, which is processed further by a Hamiltonian variational ansatz. And why we have chosen this structure, a combination of hardware efficient and Hamiltonian variational, because the Hamiltonian variational part has the gates that are chosen according to the Hamiltonian which we want to prepare the Gibbs state. And this helps in capturing the complex correlations which are appearing in the Gibbs state of the Hamiltonian. So that is why we have this part of the Hamiltonian followed by a hardware efficient ansatz as well as followed by a neural network here. So with this, we actually now I will go into few results section. So we have first observed the efficiency in the Gibbs state preparation of transverse field Ising model. And if we look at the figure B and C, we can see that as a function of parameter of the Hamiltonian, so this parameter set we have chosen such that it is not present in the training set. And corresponding to these parameters, when we look at the relative error in Gibbs free energy evaluation, it is comparatively very low. And when we look at the fidelity, which is fidelity is measured between the exact Gibbs state and the Gibbs state obtained from the meta-trained algorithm or meta-trained ansatz. And what we observe is the fidelity is also lies between 98 to or 0.98 to 1. So this has been, so we were able to calculate the fidelity and the relative error in Gibbs free energy because the system sizes which we have considered are relatively smaller. And we have also used an equal number of ancillas as the system qubits for our training purposes. So now we observe what happens when we scale the system size beyond 4 system qubits or 8 total qubits. And what we observe is actually when the system size increases, the relative error in Gibbs free energy starts to increase, and also the fidelity actually drops down when we increase the system size. This might be because the choice of the number of layers, number of hardware efficient, and uh, the Hamiltonian variational ansatz layers uh, might not be the required one, or we might not be able to understand which configuration gives us the best results. However, what we observed is when we used our meta-trained ansatz as a initialization for traditional VQT, where we are getting the Gibbs state corresponding to a single parameter, and compared it with other existing variational techniques, what we observe is our method is able to attain a good fidelity for different parameters of the Hamiltonian as compared to the other techniques. And we also analyzed the Gibbs state preparation for a model that exhibits finite temperature crossover. And for that, we have considered a model known as the Kitave ring model. And this model is interesting because the phase diagram of the Kitave ring model for finite system represents closely to that of the phase diagram which is expected at the thermodynamic limit. So the phase diagram shows like two different phases as a function of the parameter h of the Hamiltonian and the temperature. So there is a smooth crossover or smooth transition from the semi-classical regime to the quantum critical regime. So we have considered a set of parameters across this dotted line, and we observed how efficiently our algorithm is able to prepare the Gibbs state across this transition region. So when we look at the Gibbs free energy and the fidelity, so the blue color is our method and the red one is the Warkite, which I have explained briefly earlier. So what we see is our method is able to prepare the Gibbs free energy very close to the exact one, which is represented by the dotted lines, and the fidelity also stays very close to 1, unlike the other existing technique, which is the Warkite. And we also have tried to understand what happens when or how robust our method is when we increase the Hamiltonian complexity in terms of the commuting blocks, like when we add more non-commuting terms to the Hamiltonian, and observe what happens like when we see. So here we have considered neural network based meta VQT, and we observe that the precision stays or the accuracy is pretty good. So this is actually the trace distance measured between the exact Gibbs state and the Gibbs state prepared using NN meta VQT, which is our method. And this one is the trace distance measured between the exact and the Gibbs state prepared using another technique known as Warkite. So for Warkite, when the number of non-commuting terms in the Hamiltonian increases, we see that the performance or the trace distance increases, while for our method, it stays almost close to 0, and also it doesn't show any increasing trend similar to Warkite. So given this introduction to the Gibbs state preparation, so now how we can use that in the training of a variational quantum Boltzmann machine. So maybe I can actually skip this section because this has been explained as in the first talk. So regarding what are classical Boltzmann machine and what are quantum Boltzmann machine. So I will might skip the first 2 slides. Sorry, was there any question?
I think someone accidentally unmuted. Please go ahead.
Okay, yeah, sure. So I'm skipping the classical Boltzmann section and also like a brief introduction to the quantum Boltzmann machine. So which I think all of us might know. And yeah, so now coming to how how we will be integrating the variational meta variational quantum thermalizer algorithms to QBM training. So when we consider the traditional way using which the QBM has been trained, so we generally start with a ansatz where we have parameterized Hamiltonian, and the second step involves the Gibbs state preparation. And usually, from the variational perspective, we use any of the variational techniques, for example, the variational quantum thermalizer, for preparing the Gibbs state of this Hamiltonian. And this itself is a separate training loop. And once this training is done, then we will minimize, or we will try to match the Gibbs state obtained from the VQT with that of the input data, and update the parameters of the Hamiltonian. And so what is observed is, for each such iteration of within the QBM training, we need to run this Gibbs state preparation loop or VQT loop again and again, thus increasing the training time as well as the quantum resources required. So rather than that, if we can replace this pink box with our meta-trained ansatz, then we just have to give the parameters of Hamiltonian as input to this meta-trained ansatz. So we directly measure the Gibbs state out of it, and we can minimize the cost function of QBM alone, and we can do the training. So in that way, we are actually achieving a huge reduction in quantum resources by avoiding or by skipping this nested training loop, which is required for Gibbs state preparation. And we have tried it for for a demonstrative example where we have seen, or we have compared the time scales for the meta trained or the meta version of the QBM training, as well as the traditional way of variational QBM training. And what we observed is, using our method, we could actually improve the runtime by 30 times, and the Gibbs state preparation accuracy is also much higher than the existing proposal, and also we were able to achieve a lower convergence value. So though we have demonstrated it for a very simple small size example, we can see even for that small example how much time difference or how much time difference we are able to attain when we replace the single module with our meta trained ansatz. So with this, I would like to conclude with summarizing the three main points in our work. So first, we have proposed collective optimization based variational algorithms to learn the Gibbs state across multiple Hamiltonian parameters, and generalizing to unseen cases without the need for retraining. And in the cases where we scale the system size and we observe that the performance declines, so in that case, actually our meta-trained ansatz serves as better initializations for traditional VQT as compared to existing techniques. And in variational QBM, incorporating the meta VQT or NN meta VQT removes the nested optimization requirement of nested optimization loop. It supports the complex many-body models across different phase transitions or finite temperature crossovers. And we observe a runtime cut by up to 30 times, and as well as more accurate Gibbs state preparation. So this, I'm concluding the talk. And if you have any questions, I will be happy to take it. Thank you.
Thanks a lot for your talk. Very, very nice. Um, I think what we'll do is, since we went over time for everyone, I think we'll now enter the discussion session and we'll ask questions of each speaker, whichever of the speakers are still logged on, in order, starting with Nathan, then Dongling, then Ruchira. So thank you again for your talk. So Nathan, I think you're here, right?
Yeah, absolutely.
Great. Thanks so much for staying online. Can you share your slides again?
Absolutely. Absolutely. Give me a sec.
So I guess I'll
Yeah.
start by saying if there was more you wanted to say, you might have felt a bit rushed towards the end of your talk. If you wanted to take
Oh,
5 minutes or
yeah.
so and
No,
like
you
add
know what?
any other bullet
I'd
points.
much rather engage with people's questions if I've got
Okay,
the opportunity.
great. Um, we were having some questions from I think is his name pronounced Hike Gevorgian? Are you there? Um, okay, so I'll wait. I guess while we're
Well,
waiting,
I guess
if there are
does
others,
anybody have any questions?
yeah.
Yeah.
So Pratiksha,
But
Hi, can you hear me?
yes.
Awesome. So thank you so much, Nathan, for your talk. I had a pleasure listening to your talk even during the QSIM summer school, and I found it really useful.
oh,
So
cool.
I'm a fifth year PhD student and come from quantum chemistry background. Uh,
Hmm.
so um, for a long time, I have been playing with restricted Boltzmann machine, and I'm using it as a wave function itself. So you can say it's not like a traditional machine learning problem. Um, but most of the recent works in RBM have shown that with the Monte Carlo sampling and quantum simulation, they could be able to use it with the molecular Hamiltonian variationally. So I am simply using it as a wave function, and the problem that I'm facing is it usually, since I'm initializing the parameters randomly, it usually optimizes to Hadrifock like results, and it's hardly going towards full CI. So, do you have any inputs on like how this can be? Are there better approaches on initializing the parameters? I'm stuck with the BFGS solver because CMA is very expensive. So CMA was doing well, but it's very expensive for even for the 4 electrons.
So I guess a question that I have, right, is normally if you're using a Boltzmann machine, I would use something like contrastive divergence training. Why are you using something more like BFGS to estimate the gradients?
So. I'm kind of confined to use the inbuilt package, which is kind of developed to have a testing ground for such kind of ab initio method development.
Mhm.
Um, and so the way I mean initial like the way I represent the electronic configurations as like a bit string of 0 or 1 or plus or minus 1, and I am using the chemical Hamiltonians. So I haven't explored like the contrast to divergence or.
Yeah.
Mhm.
Okay, so I guess that's just a technicality, with how you're doing, the gradient optimization. The real problem is that at some level you just keep on falling into your mean field approximation that you're using a priori coming in. Um, I don't necessarily know really how to get around that problem in a kind of a coherent way. At some level, basically, though, what it's saying is it's saying that any changes that you're making to your Hamiltonian, right, are not actually improving you meaningfully beyond what you would end up getting with the Hartree-Fock approximation.
Mhm.
So under those circumstances, one of the things that I would consider doing is, looking at a broader pool of Hamiltonian operators and or looking at changing your configuration of your hidden units for this. Those are often actually the problems. The other problem could sometimes end up coming in from your training data, right? Like you may have given it training data that it's just getting confused by or are too closely approximated by the Hartree-Fox solution. So I would take a look at that in your training process just to make sure that that you're doing that all kind of well. The other thing that I've had great success with is building a um, going one step up meta beyond this, right? And taking in as input data, say the nuclear coordinates, and using that in order to be able to build a neural network to then kind of predict what the parameters for the Boltzmann machine should end up being on the other end. That is something that also can sometimes end up working for me to get around this problem. So like nesting a Boltzmann machine and a neural network to predict initializations.
I see. So in my case, I'm not particularly using any training set or something. So you can think of it like I'm just using a set of electronic configurations.
Okay.
Right?
But
Um,
yeah,
but
so in
yeah,
any case, it sounds like kind of like a little bit more of a technical thing than probably what I should be jumping into at a high level here. But if you're using it largely for regression, that could also be another one of the challenges. The objective function that you'd normally be training a Boltzmann machine for might not actually be well aligned in this case. So I'd spend some time thinking about that. It could also be a problem on that side.
I see. Thank you so much.
Okay. Does the audience have more questions for Nathan?
Hi,
I have several.
Nathan.
Oh,
Hi, Mark.
go
Sorry.
ahead, please. Yeah.
Okay. Hi, Nathan. Very nice to meet you. Yeah. I enjoyed your talk very much. Thank you very much for this very insightful and inspiring talk. So at the end of your slides, you mentioned several open questions. I remember, if I remember correctly, one of the questions is about the ultimate rule of the hidden neurons, hidden qubits, right? So I don't quite understand what do you mean by the ultimate rule? I mean, to my
Okay.
understanding, this hidden neuron basically is kind of increase the expressibility, right? The representing power, and also kind of like mediate those coupling or entanglement, something like that. So do you mean that there may be some other rules for this
Well,
hidden?
yeah.
Mm,
So I guess at a high level, right, it kind of
mm,
ends up boiling down to a bunch of different things. Like, for one,
mm,
there's even a question about whether or not, if we're giving ourselves full freedom over our
mm,
Hamiltonian, there's a question of how important hidden layer units actually are. Maybe
mm.
we'd be better off going beyond just two local Hamiltonian terms, for example, in
I
our
see.
Hamiltonian, and go to three or four or five local Hamiltonian terms. And if we
I
do that,
see.
we might not need hidden units as much in order to be able to build the correlation. And that would get around
Mm,
some of the problems of entanglement with these additional registers. But on the other hand, they would create other problems because we'd have a much more complicated ansatz with
yes.
potentially
Yeah.
far more weights to deal with.
Yeah.
And further, like we could come up with a model like what I was suggesting about building an interaction between the visible and the hidden units that
Mm,
commute with the Hamiltonian on the hidden units. That
yeah.
will guarantee that you never get any entanglement, but is there a price that you're paying along the way? And that's
I
what I'm
see.
kind of getting at, is that there's a question, well, do we need hidden at all in a quantum setting? And if we do use hidden, what's the right way for us to be able to pick our Hamiltonian? Because the eigenbasis that we're kind of
Mm,
selecting for the hidden units isn't as relevant as trying to find the appropriate eigenbasis to parse the inputs and provide the output. So
okay.
that's kind of like why I was saying that I feel for hidden units, well, I've been playing around with them a fair bit over the years. I don't feel I fully understand how they should be used.
I see. I see. Yeah. Yeah. That makes sense. Thank you very much for this. Yeah.
No problem.
Explanation. Yeah. Yeah.
Could I briefly comment? Uh, so it's like tomorrow, so like I have a talk on what you are like exactly talking about. Just wanted to say a few words. So on basically building those fully visible QBMs and their relationship in terms of expressivity to the other kinds. And after me, Maria will be talking about actually a model that like you are describing, but the other way around, if we make the classical ones commuting for classical data and keeping the hidden ones quantum, we actually show there that you can build like a relationship between how expressive you are compared to an RBM. And in a specific case, we were able to show you actually just gain like 3 times like the hidden units power by having quantum hidden units in a specific scenario. So like maybe I don't take a lot of time here because like there will be a talk on that tomorrow. So I thought it could be interesting.
Cool. Thanks a lot.
Thanks. I wanted to ask some questions. Can you advance to the slides? I know you have the paper entanglement-induced barren plateaus. You had slides about choosing the Hamiltonian
Yeah, I
randomly.
don't really like that slide, but okay.
This one, yeah.
Yeah.
I guess my question is, do you think I think there's been very limited analysis of the barren plateau problem with quantum Boltzmann machines. And if I'm not mistaken, yours might be the only paper that
To my
addresses
knowledge,
this.
it is. Yes.
And so I'm wondering if you think there's scope for more work in this direction. There's been so much analysis of barren plateaus with parameterized quantum circuits. And, are there other, I
I
think
feel
in
that
your analysis of
feel that
barren
there is
plateaus,
actually, but let
okay,
me just be a little bit more clear about the nature of the barren plateau results that we were able to show for it. One of the things is that actually the Boltzmann machine itself was kind of secondary to the presence of the barren presence or lack thereof potentially of the barren plateaus. The thing that was actually more relevant was the choice of the loss function, looking at something that was more like a quantum relative entropy between the two because of the fact that the logarithms ended up coming in. And we had situations where if you're radically wrong, right, you'd have ordinarily a low likelihood, a configuration that you'd have to estimate ordinarily. But when you put a logarithm on the outside of it, that low likelihood now is being amplified into a reasonable sized term. And that makes these situations where you're kind of in the regime of garbage, where your model isn't predicting, anything at all with a meaningful signal, that the logarithm actually can give you some ability to be able to navigate this. In the sense that when you take the Haar averages, the lower bound that you end up getting isn't necessarily exponentially small. You end up getting a lower bound, in both cases, that is only exponentially small under certain assumptions that you end up getting of the different terms, which is different than the linear objective functions, where it's always exponentially small, kind of like no questions asked. So my point about this is that, yes, the Boltzmann machine is part of it, but I think the bigger part is actually asking, when we take a look at objective functions that are innately nonlinear in nature, that depend on, logarithms of density, traces of logarithms of density matrices and other nonlinear functions of the density matrix itself, whether or not actually the barren plateau problem is as dramatic, and whether we can find necessary and sufficient conditions for it. And the Boltzmann machine then, from that perspective, is just one case that I find interesting. But even a parameterized circuit cases, I feel really interesting for those types of loss functions.
I see. Have people not investigated these nonlinear functions and barren plateaus for PQCs? There's so much literature on it that I haven't
There's not as much as
started
I
to
would
keep
have
track.
liked. Yeah,
Okay.
because I think often people are have historically been less interested in objective functions that are more generative in nature, things like relative entropies between things. But for me, because I'm most interested in fully quantum learning, that's
Mhm.
almost like the most natural place to begin. So I feel that it's been understudied. Yeah.
Um, you talked about QBMs with hidden invisible units and the quantum state learning or quantum generative modeling problem. I know there's the paper of Koopmans and Benedetti that showed if there's just visible units, then it can be done with efficient sample complexity. Do you have any expectations for if such a finding would be possible, if there's hidden units also?
I think
Looking
that
into your
one of the
crystal ball.
Yeah, I think one of the problems that ends up coming in is that the analysis, certainly on the quantum side, with hidden units starts becoming a lot more difficult because at
Mm.
some level, as soon as you have the possibility of entanglement with your hidden units, it really starts actually looking like quantum thermodynamics, where you've got this ability, the partial trace over the bath, effectively the hidden units, now ends
Mhm.
up looking just like you would end up modeling, a model for decoherence for open quantum systems. And
Mhm.
so, because you've got this problem coming in where you're potentially throwing away a ton of information through that partial trace, it becomes a little difficult to be able to show or come up with good circumstances where you can show you're not throwing away too much. So I think that, I don't think it's impossible to be able to do it, but I think that the results that would be found for hidden units will be much more nuanced and might require some very specific choices of the hidden units to make sure that you don't end up getting, exponential decays that will kill you before your analysis really even starts, or potentially requires such fine balancing of your inequalities, right? That the analysis, well, in principle, would give something sensible. Maybe everything is just looking so exponentially small, but approximately cancels, that it's much more difficult to handle in that setting.
Um, there's a question from Rahul. Rahul, why don't you unmute and ask?
Hi, can you hear me?
Yes, can hear you great.
Yeah, so my question was regarding like an application, like a potential application of quantum Boltzmann machines.
Mhm.
So like so far, like to my knowledge, QBMs have been sort of used mainly for generative modeling. I was wondering if there has been any kind of attempt to like design some kind of machine learning model similar to QBMs that solve supervised learning or regression problems?
Mhm.
And in your opinion, is this like an interesting application of QBMs?
Yes, actually, I think it is because, for one, there's a couple of ways to end up looking at it. The first is, for supervised learning, you can do it. The easiest way to do it, and this is something that Mohammed talked about also in his early papers on this, is that what you do is you kind of clamp some of the units that you're taking a look at to particular values. And then what you do is, based on those clamped values, you then carry out the evolution. The clamping, though, is more difficult in a quantum setting because clamping something to a quantum state is a lot more difficult to envision a Hamiltonian that ends up doing it than one that ends up clamping a series of bits to a particular value. So what typically I do in those sorts of circumstances is I introduce the state kind of, if I want to clamp it, I introduce the reduced density matrix as a term in my Hamiltonian. And then I can use that in order to be able to give an energy penalty to any configuration that doesn't equal the given state that I have there. And all of that you can end up building using block encoding techniques if you want to do that algorithmically. So that's how you end up doing it, but it's just much less natural than it is to clamp the units to 0 or 1 like you would do classically for it. Now, as for the other question about regression tasks, there's one task that quantum Boltzmann machines are amazingly good at from this perspective that feels more like a regression problem, and that's the problem of Hamiltonian learning. The Boltzmann machine is a Hamiltonian learning protocol. Flat out, no apologies, because what it does is it says, let's assume that I'm trained with thermal states coming in. What's the most, or samples from a thermal state? What's the most likely Hamiltonian that I could hypothesize that would generate these samples? So from that perspective, you can look at, the act of training the Boltzmann machine itself as a regressive task corresponding to a Hamiltonian learning problem. And that's something that I find really fascinating because obviously Hamiltonian learning is a fundamental task in quantum computing and control.
Okay. There's another question from Michele in the audience.
Thanks.
Please go ahead, Michele.
Can you hear me?
Oh, we can hear you now. Yeah. Now we cannot hear you.
Having bad luck.
Michele, we cannot hear you. So I'll go ahead and ask another question. Regarding your analysis of the Barren Plateau, what were the assumptions that you made on the Hamiltonian? Can you remind me of that? Like in these, there are many different interactions you can assume, and we've seen a lot about the restricted Boltzmann machine. Does your analysis apply to restricted QBMs?
Um, my my analysis, it depends on the particular paper. The first one was a restricted QBM where we ended up showing that the barren plateau due to entanglement doesn't occur if you end up picking these commuting Hamiltonians. So in that sense, yes, it's a highly restricted QBM that we're looking at because it only, A, it had the restricted structure of an RBM, and B, it ended up having hidden units going between. The next result that we're looking at the relative entropy training for it in particular, I believe that in that case, I think that we ended up showing, I don't believe we showed it for the case of hidden units. I think we showed that there was no barren plateau for the all visible quantum Boltzmann machine. At least no unconditional barren plateau for the entire Boltzmann machine.
Okay.
And we didn't need to make any deeper assumptions about the Hamiltonian.
Can you go to your last slide? I thought that was very interesting. You had so many open
Yeah, I wanted to have
questions.
more time to talk about this, but it was kind of more of a teaser than anything else, unfortunately. I could do a whole talk on this alone.
There was yeah, it was you had this long list of open questions, and I just wanted
Oh,
to see
okay,
those again.
yeah, the open question one. Sorry.
Yeah. Do you have any hypothesis about what a more efficient state would be? Like we see from like James's principle, like often
Yeah.
and like just more generally minimizing free energy, it very naturally
Sure.
emerges. So is
Yep.
there something you had in mind here?
Well, I mean, there's a couple of things that you
All
could
right.
end up taking a look at. One of them is your choice of entropy for this, right?
Mhm.
Because, from that perspective, the Gibbs state, minimizes the von Neumann entropy. But if you ended up taking a look at the optimization problem that would say minimize a linear entropy, which is a lot easier to compute and deal with, then that form of a Gibbs state might actually be computationally a lot easier to deal with.
Mhm.
Another issue that I wanted to kind of bring up is that there's also a potential that we could look at something that I'm starting to call pseudo Gibbs states. So these wouldn't be actual true Gibbs states, but they would be kind of almost like Gibbs states meets a unitary T design in the sense that they're guaranteed that low order moments end up matching the same low order moments of the Gibbs state, but the trace distance between the two states could be quite large.
Mhm.
So, if you end up saying, okay, well, the features that I want to take a look at are all based on the outputs that I want are all based on low order expectation values with a density matrix that's generated, maybe I don't care if I match the entire density matrix. So from that perspective, I'm just actually kind of suggesting that maybe we should be a little bit more creative
Mhm.
about the about the kind of onset state that we're using for this. And well, certainly the Boltzmann assumption is well motivated. Its computational headaches end up being so dire in cases that we might actually wish to shoot, theoretically, for less ambitious goals. And it may be possible to show that we don't run into some of the hardness results that plague us with the existing Boltzmann training results.
Yeah, that's very interesting. I'm curious to hear more about 4 and 6 on your list. If there's anything you wanted to say.
Okay. So for 4, one of the things that I guess I was just kind of, curious about is the role of expressivity that you end up getting in Boltzmann machines if you end up having area laws for it. So for example, one of the issues that we end up getting from the entanglement-induced barren plateau problem is a volume law of entanglement that we end up seeing in the relevant states that are included in the Gibbs state. If we ended up having something that provably ends up having an area law, then you end up running into a situation where there isn't that much entanglement between, say, distant layers with respect to, say, the graph distance that you're looking across it. But that ends up creating another question. Does that end up playing a problem with expressivity? So on one hand, presence of area laws in Boltzmann machines may end up leading to, a absence of barren plateau-like results, but may dramatically end up hitting expressivity. And the role that area laws end up playing in this setting could be really quite interesting because there may be a deeper relationship between these ideas of barren plateaus and the entanglement structure in eigenstates than what's been really explored so far. And when it comes to information bottlenecks, this is something that in particular I'm interested in because there's this approach known as the information bottleneck method that ends up taking a look at how it's originally developed as a diagnostic tool to see how information ends up flowing through a neural network about some relevant feature. But quantum analogs of this can actually be created. And further, you can end up training neural networks in order to be able to optimize the rate of information flow of relevant features through a larger network. A lot of this has been studied in the context of feed-forward neural networks, where you have a notion of time where information is propagating through different pieces as each of the gates is applied to your state. But for a Boltzmann machine, because it's kind of a static property that you're looking at, thinking about what an analogous notion of an information bottleneck through part of the graph, the Hamiltonian graph that you're looking at, is something that really I don't think I've thought about. And I'd like to understand that because if we had better sets of diagnostic tools to look at how information is kind of routed through a quantum Boltzmann machine, it may be able to provide us better insights on how to make sure, if we've got a deep network in particular, that the relevant information about the concepts that we're looking at are actually propagating in the right ways through the hidden invisible units in the Boltzmann machine.
Cool. Thank you. I think we should move on to questions of other speakers because we said we'd keep it to an hour after. So there was a question for Dongling from
Yes.
Lei Zhang. Why don't you ask your question, Lei?
Oh, hi, Professor. I just want to ask, what is the intuition for using imaginary time evolution of a single Hamiltonian to identify the ground state subspace of its expectation value? I mean, the average of many Hamiltonians.
Okay, yeah. Thank you, Lei, for the question. So, so the intuition, I mean, if you have a single Hamiltonian, like a single sample, then you cannot learn the, if you repeatedly use a single sample, right? Then you can only, I mean, you do not have enough information for instance, if you want to learn the feature of a cat or a dog, if you just have a single sample for training, then each of you just repeatedly, you remember you have a UX and then UX stagger, right? Maybe, yeah, maybe I can share my screen. So, sorry, let me share. So sorry, so in this case, right? So here you see that if you just use a single x, that means you always use the same ux, right? Then you can see this ux dagger and the ux basically cancel with each other, right? So that means you only, I mean, you only have the information about a single sample is not enough for the training. So then that's the intuition why we should go to the average. Average means like for in the next step of your training step, you use a different sample X. Okay. And moreover, if you use a single X, the single sample have a specific label, right? It is either a cat or a dog, so you cannot identify like different images. I think that's intuition. So regarding why we use imaginary time evolution, uh, I mean the motivation is that we don't want to calculate the gradient because as Nathan has explained that it is very expensive. So we want the training process to be automatically going on. So then in our case, you just start from some random state and then everything like going automatic. You do not need to calculate the gradient. You do not need to update the parameters. That's why. And then for this imaginary time evolution, you start from some random states, and suppose that your Hamiltonian has a reasonable gap between the ground state and the excited state. Then after some time of evolution, this random state will automatically evolve to the ground state, right? So that's kind of the intuition.
Yes, but the simulation of quantum imaginary time evolution may involve post-selection, right? Well,
Yes,
will
yeah, that's a
will
good
the
question.
cost of post-selection compensate for the cost of computing the gradient?
Yes, that's a very good question. Yeah. So yeah, that's intuitively after you like add this perturbation, you need post selection. Then the success probability like after several steps, it may uh, decrease exponentially with your number of n, right? Your training steps. That's I mean at the first thought. So however, as you can see uh, after you training some steps, then in the next step, you learn more and more information about your image. Then in the next step, the probability of the post-selection probability for the success case is becomes larger and larger. So then in total, then you can prove that if you choose an appropriate learning rate and the appropriate number of steps, then you can achieve a constant successful probability. Okay, so
Okay, I get it.
okay, yeah. So actually, the successful probability is basically the trace of this formula in the red box. It's just the trace of this. So also as you can see here, we in our numerical simulation we also plotted the accuracy versus the successful probability. You can see here you have a like kind of a plateaus, right? That means you can like up to successful probability like 0.2, you still have a very good accuracy. Does this explains answers your question?
Yes, thank you.
Yeah, thank you. Yeah.
Thanks for that. I think we should allow for questions to Ruchira because we're starting to run out of time. Are you there, Ruchira?
Yes.
Yeah.
Yeah.
Can you pull up your slides?
Yeah, sure.
So, there was the
Yeah.
slide on the truncated Taylor series.
Yes. This one, right?
Yeah. So,
Yeah.
throughout your algorithms that you presented later, I think you called them the meta algorithms. There was a need to estimate entropy. Is this the method you were using for that?
No. So actually, the examples which we have considered are still within the limits of we can simulate on a laptop or on a simulator.
I see.
So the number of qubits we have considered is small. So we have evaluated the exact Gibbs free energy. But when we go beyond the system sizes that are simulable on a classical system, uh, then we might means our results remain invariant if we also use this way of evaluating the Gibbs free energy. So
Okay.
like whether we evaluated the exactly for smaller system sizes or if we use the approximation techniques such as the truncated Taylor series or the second version, our results remain invariant.
So with the truncated Taylor series, I have a little
Mhm.
concern. Like, there's questions like if we know how large K needs to be to get a good approximation, but it does seem for large K, you have this sum over, you have CJ, and
Yes.
if I were to pick J equals like K over 2 as K gets large, I think that
Yes.
constant becomes pretty large, right? And
Constant
so,
will
so
just be a number.
what I mean is the CJ, like if I choose
Uh,
big K over two, if I choose J to be big K over 2, then my
uh,
concern is that this coefficient would be pretty large, and that would be scaling that
uh,
trace that you need to estimate. And so I would just have concerns about
okay.
how it would be. It seems like it would be difficult to estimate that well for large
Okay.
K, um, through sampling. I don't know if Shin or others on this paper would want to comment on that
Mhm.
point.
Yeah, it's a good question, Mark.
Okay.
Yeah. So, yeah, there will cause some problem if, like, for some cases, for large K, the number CJ maybe play a major role. Yeah, there will be some problem. And one thing I would like to comment is that um, somehow the lots of numerical experiments show that like even for small K, I mean the optimal solution is very close to the Gibbs state. I mean, even the loss
Oh,
function is not accurately close to what is the real free energy. The optimal solution, they are very close.
that's
Some,
interesting.
yeah.
So that was through numerics, like how many qubits did you do in these numerics? Do you remember?
It's a paper about 4 years ago,
Okay. Yeah.
and about 10 qubit, I guess.
Okay. It's pretty sizable.
Mhm.
Um, another question I had, Ruchira, was and I don't know if you addressed it, but in the methods for Gibbs state preparation, they were variational. And so
Mhm.
you didn't address the barren plateau issue that could arise in
Mhm.
this setting. Like my impression is that in quantum machine learning, whenever we hear PQC, we automatically
Mhm.
need to think about barren plateaus. And so I don't know if you
Yes.
commented on that in your talk.
Yeah, sure. So, yeah, I actually missed that point. So this collective, so when we talk about the collective optimization algorithms, actually we are defining like a cost function over different training like Hamiltonian parameters and somehow defining the cost function in such a way is known to mitigate the barren plateau to some extent. So it has actually been discussed in a similar paper, which is known as the meta-variational quantum eigensolver, where they are actually proposing a collective optimization optimization-based variational technique for ground state preparation. And there are also like a couple of papers around collective optimization that claims that maybe since we are defining a cost function, which is which is defining which is able to capture the properties of across the parameters of the Hamiltonian, probably it will be able to mitigate the barren plateau to some extent, but not like a definitive claims, but yeah, towards that direction. And another thing which we have tested with our algorithm is we have tested up to 8 system qubits, or you can say up to 16 total qubits. And we, at that level, it is difficult to say like whether we are observing the barren plateaus or not. We are able to train up to 16 qubits, but we have not yet analyzed whether we will enter into the regime of barren plateaus or not using our method. So that step we haven't yet done because we haven't scaled the system size as well. So yeah, so that is one future direction which we are planning to analyze. It means the scalability aspect as well as the barren plateau associated with it.
Thank you. I actually have to get running now, but if others want to stay on, and I see a question, or the recording is going to be uploaded. My understanding, the plan is to upload the recordings to YouTube to be available. Anyway, so if people want to stay on and ask more questions, feel welcome to, but I have to get running now. And thank you again to all the speakers.
Thank you.
Yeah,
Thank you,
great. Thank you,
Mark.
everyone. Yeah.
See you
Thank you, Yixin.
after a
Bye-bye.
9-hour lunch break.
Thank you. Thank
Yes.
you for organizing this.
Night break.
Bye-bye.
All right.
Yeah, have a good night.
Bye-bye. Good night. Yeah.
Yeah. Good night.
Mm.